physics. So that's the basic message of the talk. And we're going to be working in so-called 3-5 semiconductors, which you heard from Professor Alferov. Much of this work was pioneered in St. Petersburg. And so we'll be studying nanophotonic phenomena in a 3-5 semiconductor platform. And in particular, we'll be dealing with so-called self-assembled quantum dots as quantum emitters, and how their properties can be controlled and modified by the nanophotonic confinement. So you also heard from Professor Alferov that technology drives physics. I'm using my own words here, but this is really true in what I'm going to be talking about. So it's physics and technology working together to achieve hopefully new advances. So I won't read out all the names, but I'll mention my colleagues Mark Fox and Luke Wilson. Postdoctoral workers and PhD students working on the physics. These two people working on fabrication and crystal growth. And all components are equally important. So I mentioned already self-assembled quantum dots. So for those people who are not familiar, what are they? So these are nanometer scale quantum systems with very strong confinement. So what you see here, and I won't talk about crystal growth, but the growth direction is vertical. And here is an indium arsenide quantum dot embedded in gallium arsenide. And the typical size is given here is 3 by 3 nanometers high and about 20 nanometers along the base length. So the confinement is really strong. So we have strong quantization of electron and hole states. And that is critical really to the properties of self-assembled quantum dots as quantum emitters and quantum scatterers, which you'll see as I go through the talk. So we're dealing here with individual quantum dots. So the growth, we need to access individual dots, and so the growth is controlled to give a relatively low density. So we're now looking down, we're looking down in the vertical direction now, and each white dot is a quantum dot. And we're going to be accessing what I'll explain in a moment are the favorable properties of individual quantum dots. And typically the density is up to about 10 per square micron. So I've said that quantum dots have favorable properties as quantum emitters. So why are they favorable? So they behave to a good approximation as two-level systems. So they're atom-like. So they're frequently described as atoms in the solid state. So here we have a schematic of the two-level system. Here is the crystal ground state, and here is the excited state, which is called an exciton. So an electron-hole pair bound together by a Coulomb interaction. And so this is our two-level system, which we can access either by optical absorption or by emission. Now that's not enough. We're wanting to achieve circuit functions, as I'll explain in the next slide. And the circuits are mediated by interaction with photons. So we have so they would not be interesting if the quantum states did not interact strongly with photons. So it's they have strong oscillator strengths and interact strongly with photons. 3-5 semiconductors, probably most people are familiar, have a very well-developed fabrication technology, including, for example, in this laser pointer, but many, many examples. So a well-developed nanofabrication technology. They emit single photons on demand. So when an exciton recombines, it emits one and only one photon. So they act as single photon sources. They have favorable spin properties, as we'll see. So optically active, we can address spin properties of the quantum dots by optically. And it's in principle a scalable technology. And we're going to be dealing with indium gallium arsenide quantum dots in a gallium arsenide matrix, basically because that's the best developed quantum dot system. So here is an artist's impression of a quantum circuit. So what we're trying to achieve is on-chip quantum optical functions. And I'll show you real examples as we go through the talk. But here is an artist's impression. So here you have what's called a directional coupler, and these we term nanobeam waveguides. So this is an on-chip version of a beam splitter, and is a way to entangle two photon states, for example. So here we have the directional coupler, and this is interfaced with a photonic crystal. And I won't have time to describe photonic crystals in detail, but photonic crystals enable us to control the radiative properties of quantum states. And by doping the structure, by making a p-n junction, we can apply electric fields, which provides further measure of control of the quantum states. So here it's shown schematically applying either a lateral electric field or vertical electric field. And I'll show you examples of that later in the talk. So, and I'll just say it once again, everything is on chip for integration and scalability. Now that, as you'll see, brings its challenges, trying to achieve all the functions on chip. But I'll also show you that I believe we can overcome these challenges. So that was a schematic diagram of a quantum circuit. So this is an experimental realization. So it's essentially the same type of circuit as I showed you here. So here is the nanobeam waveguides, the photonic crystal, and these are so-called outcouplers. So if light propagates along this arm here, it's scattered by these outcouplers and can be detected externally. So this, and we deal always with single mode waveguides, which is important for quantum optics. So that sets a small length scale of 150 to 300 nanometers. So that's the nanophotonic aspect. And so this is the structure as it's grown on gallium arsenide with aluminium gallium arsenide sacrificial layer, and then the waveguide region with quantum dots embedded at the center. So the quantum emitters embedded at the center. And we remove this so-called sacrificial layer by wet chemical etching and create suspended structures of the type you shown here. So this gives us, so this is air above them on all sides of the directional coupler. So this gives us very large refractive index contrast and very strong optical confinement. And typical sizes of the structures that we can easily make are 20 to 30 microns. So I'm going to describe three topics, or three principal topics. So the first one is so-called spin-to-path conversion. So I've already mentioned that we can access the spin properties optically. So is this useful? And the goal, and it is very useful, but because our architecture is all on chip, the important question is, can we transfer spin information on chip? Can we convert spin information to so-called path information? So, and the answer will be yes. And this is now a route. If you imagine two quantum dots or two quantum emitters, we want them to be able to communicate to create a circuit. And to be able to do this, we need to be able to transfer spin information in the plane on chip. And here are two references where some of this work is described. So the first thing we do is apply a magnetic field in the vertical direction, the so-called Faraday geometry. And this splits the exciton states into two, so spin up and spin down. And if we observe vertically, these correspond, these emit circularly polarized light, and right circular polarization and left circular polarization. So this is all, so this is the Zeeman splitting, and which results in sigma plus and sigma minus photons being emitted vertically. Now, what we want to be able to do is to transfer the spin information. So, and this shows the Zeeman splitting as you apply the magnetic field into the two components which are observed vertically. So the first question you ask yourself is, can this circular polarization information be transmitted in the plane? And because if you think just for a moment and think back to student physics, undergraduate physics, if you have a circular dipole and observe in the plane, then if this was an atom, this would be linearly polarized. So all the circular polarization information is lost. So the question is, can we transmit the spin information in the plane? And the answer to this question is yes. This is generally termed chiral behavior, and it is, as we'll see in a moment, it's a general property of nanophotonic confinement. And here is a definition of chiral for people who are not familiar. So an object is chiral if it is distinguishable from its mirror image. So, and the reason we can transmit circular polarization information in the plane is that in laterally confined structures, nanophotonic geometry, circular polarization is supported. And this is because both the transverse field, which is true in an unconfined structure, the EY field, and the longitudinal field are both non-zero. So that's the key point. When you confine the structure laterally, there is a non-zero longitudinal component, and with a pi/2 phase difference. So this is the requirement for circular polarization. So this shows a simple solution of Maxwell's equation. So the red curve here, so here is the center of the waveguide along the y direction. And what you see, the red curve, the transverse field is non-zero at the center of the waveguide. The longitudinal field is 0 at the center of the waveguide. And so the transverse field decreases with distance from the center. The longitudinal field increases. And what we call the circular polarization component, the amplitudes are equal. And what's also critical is that they have a pi/2 phase difference. And the sign of the phase shift depends on the direction of propagation. So just to remind you then, we've got EX and EY both non-zero with a pi/2 phase difference. So that is the definition of circularly polarized light. So in the nanophotonic geometry, we support circular polarization. And so at the C points, we have coupling of the spin states to the propagating mode. And these are electromagnetic simulations, so finite difference time domain simulations. So where we put a sigma plus dipole at this point, at the C point, at the circular polarization point, and a sigma minus dipole at the same point. And what you see is that the sigma plus dipole propagates to the left, and the sigma minus dipole propagates to the right. So the simulations tell us that we can indeed transmit spin information in the nanophotonic geometry. So this is all very well. What is found experimentally? So this is now for a dot. So let me also say, so it shows chiral emission. And the chiral behavior, it's in a non-chiral structure. So the waveguide itself is inherently uniform. It's the electromagnetic field which shows the chiral properties. So here we now have a nanobeam waveguide, a very simple structure with a quantum dot at the center. And we observe vertically first of all, and we see sigma plus and sigma minus components. And then if we detect from the right out coupler, we see just the sigma minus component. And if we detect from the left out coupler, the red curve, we see just the sigma plus component. So we have very good, so in other words, sigma minus goes right and sigma plus goes left. So we've achieved very good spin to path conversion. So the original question I posed is answered very positively, that we can indeed transmit spin information in an on-chip geometry, and which is the basis then of creating spin-based quantum circuit. which is what I've summarized on this slide here. So it's a route to in-plane communication between spins in an on-chip geometry. So that was the first topic I was planning to discuss. The second topic is very recent work that is, and if people want to read about it, you can read about this very soon, about to be published. So here we have a more complicated structure. So we have a quantum dot embedded in a photonic crystal, and I'll say more about photonic crystals later on. It's again a thin gallium arsenide membrane, and we have a vertical electric field, and the photonic crystal provides the so-called Purcell enhancement, which I'll be talking more about in a few minutes. So enhances the radiative properties of the quantum dot. And what we're going to be probing now are nonlinearities at the single photon level. And so the basic experiment is we shine in a weak laser beam, so coherent light, and which is transmitted along the nanobeam into the photonic crystal waveguide, and that is detected in transmission, or is detected externally. And we can probe the quantum dot properties, so the quantum dot scatters the single photons, which we can then detect either in transmission or reflection. So we're now working at very low photon numbers. And so if we ask what happens at low photon numbers, so here is our two-level system, the quantum dot, in the single mode waveguide. And the incoming light is the coherent laser beam, which has a Poissonian distribution. So single photons, two photons. Single photons are reflected, are backscattered, and two photons are transmitted. And the two-photon transmission is often or sometimes referred to as a photon-photon bound state. So what's happening here is the first photon comes, because we've got two photons so the first photon comes in, excites the quantum dot, and a second photon then arrives and stimulates the relaxation of the first photon, so leading to what is sometimes termed a photon-photon bound state. You can also think of this as the single photon being reflected as a single photon filter or sorter, and then two photons being transmitted. So now this is the experiment once again. The laser beam is incident on the left outcoupler, transmits through the waveguide, and then is detected at this outcoupler here. And what we see is very strong modulation in transmission. So remember, this is a single quantum state. So just one individual quantum dot is giving rise to very large change in transmission of the weak laser beam. So in this case, up to 40% modulation of transmission. And I'll mention in a few moments even much stronger modulations. But this is achieved by the very strong nanophotonic confinement, very good coupling of the light to the single quantum system, and the very favourable properties of the quantum dot. So again, I haven't got time to go into details, but we have narrow line widths which are very close to the intrinsic properties that we expect from the quantum dot. So it's a combination of the favourable quantum dot properties and the strong nanophotonic confinement. So that's in transmission, the same results I've just shown you. We can also measure in reflection, and so now we see a peak at the same energy as the dip in transmission. Now time is going on, so I'll be quick here. This is a slide on so-called Hanbury-Brown twist measurements, which probes the quantum dot, the quantum optical properties. And the basic point is that I'll only talk about anti-punched photons. So if we have a single photon source, or a uniform stream of photons, then which is incident on a beam splitter, and then we have two detectors. If it's a single photon source, then if we detect a photon with detector 1, then there should be no signal on detector 2. So that is so-called anti-bunched light, and the so-called second-order correlation function tends to 0. So that's what we expect for the back-reflected photons. We expect the so-called G2 function to tend to 0, and the transmitted light should be bunched with G2 greater than 1. So that's indeed what we find. If we now measure the G2 function, we see G2 of about 1.15 in transmission, and a G2 which is tending, which is not 0, but is tending, is below a half, which is a single, shows that single photons are being reflected. So 2 photons are being transmitted, single photons reflected. In more recent work, which I'm not showing today to save time, we have achieved much better or even stronger light matter coupling, and with dips up to 80%, so nearly complete extinction of the transmitted laser light by the single quantum dot, and very strong bunching. So the final topic is approaching the transform limit. So this is said in a different way. Can we approach ideal properties of the quantum dot in an on-chip geometry, which is what we need to achieve large-scale quantum circuits? So we need high coherence, and we want each photon to be the same, so indistinguishable. But this may be hindered by dephasing effects. So I've only spoken about advantage of nanophotonic geometry. There's the disadvantage is that the quantum states are relatively close to free surfaces, which may perturb the properties of the quantum dot. So there's a general question that it may be hindered by dephasing due to the close proximity to surfaces. What you'll see is that this is actually not a drawback, that we can overcome this. In fact, it's not a limitation. And which you also could have guessed from the single photon nonlinearity work that I just presented. So to be more precise, so the coherence time, this is a familiar expression to some people. T2 is the coherence time. T1 is the radiative lifetime. And what we want for indistinguishable photons is, and T2 star is what's so-called pure dephasing time. And what we want is for T2 to be determined by radiative recombination. So T2 equals 2T1. And the way to achieve this is to reduce T1, to make T1 small, so that T2 equals 2T1. So that any effects due to T2 star are negligible. And we achieve this by the so-called Purcell effect. And the Purcell effect, or Purcell factor, is the so the Purcell effect is that spontaneous emission, the rate of spontaneous emission depends on the density of final photon states. So if we can increase the density of final photon states, we can enhance rate of radiative recombination. And we can do this by embedding the emitter in a photonic cavity. So the Purcell factor, which is the ratio of the lifetime outside a cavity to inside a cavity, is given by the Q factor of the cavity divided by the volume. And if you, simple substitution for a very small cavity predicts Purcell factors of about 100. Up to our work, the maximum reported Purcell factors were about 10. And again, within the limited time available, I can't describe all the details, but by developing new measurement techniques, we're actually able to measure Purcell factors up to about 40. So it was not that the Purcell factors were limited by 10, it was the difficulty to actually measure very large Purcell factors. So this is the type of structure we're dealing with. So here is a photonic crystal with one missing hole. So this is the cavity. So the volume is very small. And because we're dealing on chip, the modes of the cavity are coupled to waveguides, which are then detected externally, or the photons are detected externally. So these are the two modes of the cavity. And what you see is by applying electric field, we can tune the quantum dot across the energy or the wavelength of the cavity, which is the vertical line here. So again, in the time available, I won't describe the new techniques, but let me simply say that by using very high time resolution techniques, we can actually measure the radiative lifetime, or the lifetime of the quantum dot in the cavity, and it's extremely small, so it's about 20 picoseconds. So that corresponds to a Purcell factor of 30 to 40. So we have record low radiative recombination times by embedding the quantum dot in a very small volume cavity. And to show that this is indeed a real phenomenon, so I've already mentioned we can tune the quantum dot through the cavity. Here is the cavity mode once again. We can, by applying electric field, we can tune the quantum dot through the cavity mode. And what you see, so if it's perfectly on resonance, we have the Purcell factor of 40. And then as we apply electric field and tune the quantum dot away from the peak of the cavity mode, we see that the Purcell factor decreases in a way exactly as you would predict from the width of the cavity mode. And then finally, the proof that this is useful leads to the quantum optical properties that we desire. So here now we're doing, again, Hanbury-Brown-Swiss second-order correlation measurement, and so the signature of a very pure single photon source, as I've already explained, is a very small signal at t equals 0, and that is indeed what we find. So a very high purity, so the G2 is essentially 0. So we have a very high purity, on-demand, single photon source. How am I doing? Yeah, so I'm nearly finished, yeah. So we do indeed have a very high purity single photon source. This is a bit technical, so I won't go into it. And then finally, I said that the goal is to achieve indistinguishable single photons, and this is probed by so-called Hong-Ou-Mandel two-photon interference, and again, this is a purely quantum effect, so if two photons are indistinguishable, then they coalesce. And the measure of this is the so-called visibility, and which is very high for our strongly Purcell-enhanced single photon source. So we have values up well in excess of, or tending towards 100%. So high indistinguishability, single photons on chip. And we've achieved this by, to say it once again, by the Purcell effect. So we've reached very close to the radiative limit where T2 is determined by population decay. So it's determined by intrinsic properties of the quantum dot and not by dephasing effects in the environment. So we've made T1 very much smaller than any effects of pure dephasing. And in separate measurements, which we do indeed find that T2 is equal to 2T1. And as required to obtain a stream of indistinguishable single photons. So I've shown you, to come to the conclusion, what I've tried to show you is 3 examples of nanophotonic phenomena leading to new optical and quantum optical functions. So the chiral behavior, the Purcell effect, and the single photon nonlinearities. And none of these are achievable without the strong nanophotonic confinement. The question I posed in the final part of the talk, can we achieve coherent single photon sources on chip? The answer is yes, and in particular by taking advantage of Purcell enhancement, so modifying the radiative recombination properties. And this opens up a route to nano-optical waveguides, or the nano-optical waveguides are a route to spin or communicating spins on chip and more complicated quantum networks. So thank you very much.
We are very limited in time, so we have time just for one question, and let me use my privilege as a chairman of the conference to answer this question. So everything you talk about operates at a very low temperature. So is there any chance to operate at room temperature? Because as I understand, the non-radiative recombination and quantum dot homogeneous broadening also very dangerous for operation at room temperature. So what's
so this is very likely a low temperature phenomenon, because even if you go to, say, gallium nitride systems, which are more stable at room temperature, the coupling to phonons degrades very strongly the coherence properties. So if you want to retain, so it depends on the goal. If you want a single photon source, maybe high temperature. If you want high coherence, you need low temperature.
So no chance for gallium arsenide and indium gallium arsenide to operate at room temperature, for the moment at least. Yes.
No, because in all systems you couple to phonons if you raise the temperature.
Okay, thank you. Давайте благодарим еще раз докладчика. Спасибо большое. Я с удовольствием представляю следующего докладчика, Штефана Броера из Технического университета Дармштадта, Германия. Его доклад называется Stability of Semiconductor Laser Optical Frequency Comb. Stefan, please.
Excellent opportunity. Thanks very much to the organizers for inviting me to this international school and conference. I'm working as an experimental physicist and engineer in the Institute of Applied Physics at Technical University of Darmstadt. And in this talk, I'd like to address a few topics on the stabilization, or especially the improvement of the mode spacing stability of frequency comb lasers that are based on single section and multi-section semiconductor lasers. So here, for example, you can see one of these lasers operating in some kind of contacting here with injection current and reverse bias, and there's even some light coming out. The wavelength is around 1250 nanometers, so all results we will see will be either at 1250 nanometer wavelengths or at 1550 nanometer wavelengths. What is the motivation behind investigating ultra-fast semiconductor lasers for the generation of optical frequency combs? And this is driven basically by a multitude of applications, including chemistry or biology, where you can think, for example, of spectroscopically detecting multiple transitions in a chemical if you have stable combs of your optical source. For example, in telecommunication, where it's favorable, as we will see in the motivation, to have a fixed set of different colors, where with each color you can transmit individually your data across short or long optical distances. or for example, signal processing like digitalization processes. However, if you're looking into frequency comb sources that generate pulses with high peak power, a very nice motivation is also the multiphoton fluorescence microscopy, where you need a delicate balance between high average power and high peak power of your source. But the particular advantage would be to have a very compact device, a few millimeters long, that would be able to do this 2-photon emission fluorescence microscopy experiment. And there's radio frequency generation. When you have a pulse train in a semiconductor laser, it has a round-trip time. This round-trip time corresponds to a fixed frequency, and this fixed frequency depends solely on the laser length, of course, which means a millimeter-long laser will give you a 40 gigahertz radio frequency signal if you convert your optical signal into the frequency domain. And this is one example here where such a pulsed laser, a very short quantum dot mode locked laser in this case, has been interfaced with an antenna where just this round-trip frequency of the pulse train is transmitted into free space, for example, for communication application. There's also another very strong motivation to look into the frequency stability or the comb spacing stability, and this would be a time-critical application towards optoelectronic oscillators. If you imagine you have your laser source with a pulse train inside generating a lot of optical modes, then you generate a quite pure frequency or higher harmonics of this frequency. And this, for example, comes into play in microwave and millimeter wavelength applications in the gigahertz region. For example, a photonic radar. There has been a demonstration by an Italian group here in 2014. For example, in signal processing, sensors, or even metrology. So the common implementations to achieve this very high spectral purity or frequency combs involves optical phase-lock loops or semiconductor nonlinear laser dynamics, where you exploit, let's say, the interaction between two narrowband semiconductor lasers to generate these kind of beating signals. But ideal would be a simple, compact, single-chip semiconductor device that would generate gigahertz radio waves, and ideally without supermode noise, so which means you generate just the repetition rate frequency and higher harmonics, but the rest is without noise. So without supermode noise ideally. So low amplitude and phase noise, which means it's the jitter basically between the individual comb lines, which gives you a spectral motion. So high spectral purity. And one of these approaches would be to explore the potential of quantum dot mode lock lasers and different stabilization concepts to improve this comb stability. And ideally would also be an understanding of this reduction, because there are several approaches to explain it, but I hope to be able to present you a quite simple picture and a quite universal one that allows to explain that improvement in stability. The last motivation is optical data communications. So where typically you have interdata links, for example, or links in between different data centers. And essentially there you have multi-wavelengths, you need multi-wavelength sources which are coupled into a waveguide and then transmitted and at the end decoupled again, so multiplexed and demultiplexed on the receiver side. So how is it done? Conventionally, worldwide, you have different narrowband semiconductor lasers, DFB lasers. Each of these lasers provides you one stable wavelength, one stable color. But of course, on the other hand side, has been stabilized also by temperature tuning to keep the mode spacing between the individual colors fixed. And then they're coupled into a light waveguide here, and you have all the colors inside the waveguide for the transmission. So what would be really cool is if you would be able to replace all these sources by a single source, and now you can already see why a highly stable multi-color, multi-frequency semiconductor laser source would be ideal in that case, is of course because exploiting the particular multi-wavelength emission of quantum dot lasers together with the locking of these modes, because otherwise the comb would just jitter in amplitude, so the different colors would be just too noisy in amplitude, but also they can do something like this, which would mean dynamically changing the mode spacing, which like a conventional multimode semiconductor laser would do. This is of course not what's required. Required would be a highly phase stable comb without or let's say with as less as possible amplitude fluctuations. There are some certain demands, of course, which first of all are the wavelengths range. So we're working at 1250 because we have only recently got access to 1300 nanometer quantum dot gain material since November last year, but also 1550 nanometers, of course. So multi-wavelengths would be ideal to generate between 10 and 100, with ideally a fixed frequency separation. So depending on the different data, let's say architectures or data transmission architectures, you have different frequency spacings. They are fixed by some standards. One of the most common standards would be 40 gigahertz. As said already, lower relative intensity noise, it's just these fluctuations of the amplitude is required, and the phase noise is just this kind of spectral motion, and the motion of the total comb. Optical line width requirements, RF line width requirements, and depending on the application, you also want to have a dynamic frequency spacing, so to be able to dynamically change the mode spacing. As we already have, let's say, motivated, the laser length gives a repetition rate, so which means at first instance it's fixed, so no tunability at all, but we'll see certain concepts to get this dynamic frequency spacing. So overall goals would be to investigate and finally to design, to realize multi-wavelength frequency comb sources as a monolithic laser chip, just a single chip. Then to exploit different frequency comb stabilization concepts on these kind of lasers, to be able to control the comb spacing, and finally to reduce the sideband noise. And the final goal will be to develop an understanding why, especially in classical two-section or multi-section semiconductor lasers, and in single-section semiconductor lasers, where you can attain this phase locking to generate stable mode comb, why it's happening. Because essentially, since 1970s, I would say there are around 4 different explanation approaches, theoretical approaches to explain why in a single-section semiconductor lasers you can generate a phase locking of the modes. As far as I know, none of these have been proven experimentally up to now. There has been a new theoretical explanation reported 2017 by a group in Politecnico di Torino. We team up with this group since 2006 actually, and we hope to be able to provide a small insight, not yet the final explanation, but a small insight what could happen. We are on that way. So the mechanism is still unknown up to now. Okay, so the content would be to present you a selection of low-dimensional lasers, that is quantum dot, quantum dash material lasers, for the potential as alternative compact sources for these time-critical applications, as optoelectronic oscillators and multi-wavelength sources. And in particular, we look at single-section and multi-section lasers towards the control of the comb spacing, the spectral motion of the comb, so which means this dynamic spacing, and the movement of the comb itself. So these are the 2 critical issues, and with a simple explanation approach. If you want to generate a optical frequency comb with semiconductor light sources, there are different approaches, and this is of course just a selection. So you can generate, for example, you can modulate your laser electro-optically to generate broad frequency spectra. Sorry for the small picture, this is all 1550 nanometers. You can employ, this is a hot topic, evolving quickly, microresonators that are injected with a highly stable semiconductor laser. And also here at the academic university, Professor Chukov is pioneering this. Microdisc structures in semiconductor materials. It's, for example, optical injection of vertical cavity surface emitting lasers. Actually 2 startups right now in Europe that are commercializing a very simple technique. It's actually a vertical cavity surface emitting laser. So just this, with a narrow aperture, like 10 micron diameter. And what they do, they just electrically modulate this VCSEL with a rectangular current form, and this gives a stable frequency comb. So they can package it like this. However, well, it's there within the commercialization. The second group is in Spain. It's here the group of Prior. Or that's a concept here developed for a two-section mode-lock laser is a dual mode injection, where you basically have a mode comb that can jitter some around or jitter like this, but you can set a single, you can eject a mode here, then you say to the laser, hey, stop please with the jitter, and the laser just, I mean, this mode will be fixed, the others will be jittering, but if you inject a second mode here, then of course the laser has no chance at all to jitter anymore, because these two fix the separation. This is this concept basically here. Okay, so just to recap, what is necessary in the ultra-fast semiconductor lasers to generate a mode comb or a phase locking of the modes, and this is in a conventional two-section semiconductor laser, the passive mode locking operation, which essentially involves an electrical isolation of your top contact here, in applying a reverse bias, minus 10 volts, for example, a DC voltage, and injecting here a forward current into the gain section. Essentially what happens is a mode locking of the longitudinal modes in this device, and a pulse is evolving. So you can see here picture simulations by Team Turin. So you have here the absorber section, the gain section, here's the output facet, here's the back facet, the pulse is here reflected, then increasing in intensity, then there's a pulse coming out, and back and forth and back and forth. So it's essentially such an absorption process in the absorber that leads to the pulse shortening, and an increase in amplification that leads to the pulse peak power increase. What happens in such a laser if you don't have this electrical isolation, as in the single section lasers? So this is a two-section laser, just remove this here, and you have a single-section laser. Then you would say, well, you have a conventional Fabry-Perot cavity. But in the scientific community, there are two very successful approaches. The one is by LPN CNRS in Paris, Professor Ramdan. The other one is by Philip Poole at an institute in Canada. They are able to generate a fixed length of the laser, which is always below, well, 90% always below 1 millimeter. And if you do that, you can phase lock your modes. So there's an effect which is sometimes called magic mode locking. It's sometimes, the effect is sometimes called self-mode locking. And there are 3 approaches or 4 approaches to explain how these modes are locking, but still the effect is open. So in the conventional passive mode locking case, you need, let's say, a dynamic state of balance for the gain and the absorption. So this is the time here, that's just a simulation picture. So the absorption needs to be high, needs to be saturated here by the gain. Then if it's saturated, you generate a pulse. And of course, you can see if these kind of, these time constants do not fit properly, this gain profile can be subject to different disturbances, like, for example, leading edge or trailing edge instability. So as far or as soon as there are leading or trailing edge instabilities, you find that the pulses deviate in position, and this immediately translates to a change in the stability of the mode comb. How to describe this mode comb stability in time and the mode spacing stability? And this is a simple picture basically based on the period instability. Just imagine out of your two-section laser, out of your single-section laser is a pulse train emitted, and this pulse train has ideally a fixed spacing between the individual pulses. However, because we have a semiconductor gain material, there are round-trip phase errors, and they add, basically they deviate, they generate deviations between the individual pulse positions with respect to this ideal reference clock. And this is mainly due to amplified spontaneous emission. This kicking back and forth the optical pulses in the laser. It scales here also with the energy, or square root of the energy, as explained here by Paschotta. But the important point is here, we can regard this free-running, the semiconductor laser, this ultra-fast semiconductor laser, as a free-running oscillator subject to uncorrelated timing noise. And this means it accumulates these kind of round-trip phase errors by each round-trip time. And important is also this non-stationary characteristics of the timing jitter. And with this, there's a measure, which is the timing jitter, pulse-to-pulse timing jitter, which is just dependent on your fixed mode comb spacing, the frequency, which is given by the length of your laser. So 1 millimeter semiconductor laser, 40 gigahertz repetition rate, 40 gigahertz mode spacing. And this is just basically the width of this frequency line, 40 gigahertz fit, and the 40 gigahertz as a repetition rate here. And if you want to do that, characterize it, you can take your laser, detect the optical signal with a radio frequency or with a high frequency detector, and convert it to the electrical signal, observe it on an electrical spectrum analyzer, and you will see a power spectrum like this. So this is the electrical power, this is the frequency, and in this case the laser has a fundamental repetition rate of 10 gigahertz. These are simulations also, and you can easily see that if we increase the timing jitter, so the black one would be like this, a discrete mode comb here in the radio frequency regime. If we attribute different degrees of timing jitter, we see that this line gets broader and broader. And this is exactly what we saw before in the simple formula. Conventionally, if you look in literature, it's done with the von der Linde method, which is a very famous method to investigate this stability. So let's take a look. How can we influence the dynamics mode spacing here? And how can we stabilize the spectral motion of such a frequency combed out of a two-section or a single-section semiconductor laser? And there's quite a variety of techniques around. Some of them are very famous here. For example, the hybrid mode locking, where you inject an electrical signal. Let's say you have a 1 millimeter laser, you inject 40 gigahertz radio frequency signal into the laser to pin the mode spacing. Or for example, optical pulse chain injection. So you have a second laser which has a more stable optical frequency comb. You inject it into the slave laser here. Or optoelectronic feedback, multi-absorber colliding pulse techniques that we have recently developed. And let's just pick out 3 of them because they can be extremely nicely connected. And I hope they will show that the reason or the underlying mechanism can be explained in a very simple manner. So in this case would be hybrid mode locking. So we modulate the absorber with 40 gigahertz, for example, to stabilize the comb. An optoelectronic feedback case where we couple out part of the light and inject it back into the absorber section, or all optical feedback. And this is just self-referencing part of the optical light of the laser back into the laser itself. And this is independent, of course, if you investigate a two-section or a multi-section or a single-section laser. And ideal would be, let's say, an explanation for the effectiveness of all approaches. And we have to make 2 hypotheses. And this is essentially that there's a round-trip phase averaging effect inside the lasers. We have the gain and the absorber dynamics. And that the pulses that are emitted and coming back from the outside will have a certain position or a certain range where they can interact with each other. And also we need to assume statistics from the past so that we have a partial statistical independence of the pulses inside the laser and outside the laser. And the basic idea here is expressed by this inequality here, which is saying basically that the mean value of 2 random number series has a smaller standard deviation than the mean value, or there's a standard deviation as a standard deviation of one of the individual random number series here. So let's just recapitulate. So we have seen this kind of pulse deviations with respect to the ideal period. And these basically add up as small deviations here in time. So this is basically a random walk process. And this can be quantified here by this timing jitter, pulse-to-pulse timing jitter. As we have seen, just Fourier transforming this time signal into the radio frequency domain allows us to give this 1 over f squared dependence, as we have seen, which is also valid for the von der Linde method for a directly modulated laser. So the sole modeled quantity in that case is deviation of the round-trip time and the round-trip phase of the pulses. So there's no other active region ingredient. So it's a discretized differential equation, assuming a random walk process. with a it's numerically calculated, and what is coming out of the simple stochastic model is the phase noise power spectral density, or we can do the Fourier transform also. So first case we'll take a look on is for the hybrid mode locking case. So we stabilize the laser here with an electrical source matching the comb spacing of the semiconductor laser. And this can be described just as the free running laser plus a timing noise strength here and an interaction strength like a restoring term. In this case, this hybrid mode locking function is known, and we can compare this to the experimental result here. So this is a timing phase noise power spectral density, a measure for the spectral motion stability of the mode comb as a function of the offset frequency. And you can see here the experimental part as the solid lines here for different electrical injection powers. So the higher the injection power you can see, the lower the better the stability, the lower the phase noise here. And now the only thing that needs to be done is adjusting this gamma parameter here, this timing interaction strength, because we don't know it. It changes for every semiconductor laser, for every active material. We need to adapt this, but it can be nicely done. And if it's adapted once, you can find this quite nice correspondence. So we see the impact, and it can serve us as a kind of calibration for the measurement. What we can see is that there's a timing effect verified by this approach. The question, of course, is what happens if we investigate the all-optical feedback. Before we do that, we look at a combination of opto and electrical feedback. In this case, we collect the light here, send it through a fiber, detect the light, and then just pick out the fundamental repetition rate, so the comb spacing frequency, and inject it via bias T back into the absorber section. So which means, for example, for 8 millimeter long laser with 5 gigahertz, that's an ideal laser to do this experiment. You have 5 gigahertz electrically that can be conveniently detected and injected back into the laser. So in that case, we have to include here a round-trip phase averaging term and the delay term, of course, of this external cavity here. So it's some kind of self-delayed or delayed self-modulation. Again, in the timing phase noise power spectral density, we find quite well agreement. And if you look close here, around 10 megahertz, you see a small deviation here. And this small deviation is the sideband noise resonances that are induced by this external cavity, which is quite nice because it also confirms this statistical effect that we assume. We have the 1 over f squared dependence, so that is still quite nice. Now the final step would be what happens to the all optical feedback, which is immediately applicable to single section and multi-section lasers. And for this, we introduce some kind of overlap weighting factor here in the formula that is just saying that the pulses can interact if they are close enough to each other. And this overlap weighting factor is just a Gaussian function. So if you do that, and if you look at the timing phase noise power spectral density, you get this very beautiful noise resonances here that you always get if you do single optical feedback. And it's exactly the external cavity frequency here of your stabilization circuit. It matches already quite nice, but if we include the pulse widths into the model, then they are even more nicer reproduced. So with this, we can assume a purely optical interaction, and we can verify this noise resonances. This I will skip in the sake of time. Let's come to the quantum dash laser results. So this is one of the quantum dash lasers from LP and CNRS in Paris with a quite stable, with a quite nice ripple here, or low ripple. And in this case, we exactly do the experiment. We use a laser, we delay the optical light, it's fiber-based, into the laser, and we exactly do this optical feedback experiment as discussed before. Laser emitting at 1573 nanometers. And if you compare this result, so this is just a change in the mode spacing, so it's just this change which is dynamically possible to the optical feedback delay. This is the optical feedback delay. It's possible to change this mode spacing dynamically and also reproduce it with the simulations, which are in black, quite nicely for strong and weak optical feedback. However, this single optical cavity induces noise sidebands. This is exactly seen here. So the fundamental repetition rate is 20 gigahertz, and this noise resonance appear here to the optical feedback, as we know. And I will skip this beautiful experiment. However, I would like to show you the extension from one optical cavity to two optical cavities. With a simple model, we can predict that the noise resonances can be considerably reduced. Actually, with 3, they are completely below the noise floor. We haven't checked, but the model is telling that to us. And I will just skip this also. No. But this is exactly the mode spacing control now here with the delay of the one optical cavity, the delay of the other optical cavity. And as we have seen, with single cavity, we have the 40 gigahertz signal. We induce the optical or the sideband. The noise resonance sideband is in the radio frequency domain. We don't want to have this for the optical mode comp. And this is a map showing that the dual optical feedback can reduce this noise-induced side resonances completely. And just to give you the picture, the final picture for the dual cavity optical feedback for a quantum dot-based single section frequency comp. This is a 1 millimeter long 40 gigahertz laser. You can see the optical comp here. Mode spacing of 210 picometers. This is the experiment. You can already guess what happens. So you have 2 external cavity feedbacks applying to this optical frequency comp. And this is a final experiment. So what we find is, again, the change in the mode comp spacing frequency as a function of the delay of the one cavity, as a function of the delay of the second cavity. And this gives you around a tuning range of 50 megahertz for a single section frequency comp laser. And these are simulation results with this stochastic model presented, which allow us to reproduce these results with qualitative agreement. However, we have to assume an interaction width of 8 picoseconds. This is typically the optical pulse width. In this case, it's a single section laser which emits this phase-locked modes. But due to dispersion, there are no pulses coming out because they're just too broad, giving you a CW output of the laser. So 3 optical cavities would be ideal. This is the experiment we are working on at the moment. It's not yet small enough because we will still be influenced by external influences like noise, acoustic, vibration. So we submitted our very first photonic integrated chip here to a multi-project wafer run, which will essentially look like this at the end. It will be hopefully coming in May. So we try to implement so we designed that with a simple model. We try to implement all the different stabilization schemes on one chip, and hopefully we'll be able to demonstrate together with the macroscopic experiment the validation of the model. So with this, I would like to thank you for your attention, and I'd like to thank especially the group here at TU Berlin, CNRS, Polytechnic of Torino, Inolum, and especially the RFBR and the DFG for funding the work starting this year. Thank you for your attention.
Thank you. Okay, Stefan, unfortunately we should skip the questions. So I hope everyone who are interested in this topic can ask questions during the coffee break. So thank you once again. And I would like to introduce the next speaker. Here is Professor Ewan Liu from University College London, and his presentation is entitled 35 Quantum Dot Materials and Lasers Monolithically Grown on Silicon Platform.
Good morning, everyone. Can you hear me? Thank you much, Chairman, for your kind introduction and your invitation for me to here to show some results we developed recently. My name is Huiyun Liu from University of London. My talk mainly on develop 3.5 quantum laser on silicon platform. The first thing we want to talk why we want a laser on silicon. After that, I will talk the limitation of group 4 lasers in the history. After that, I'll talk about the 3.5 laser on silicon, what we developed in the last 30, 40 years. Eventually, I will talk about what's our idea to develop 3.5 quantum dots technology with 2 approaches. Finally, I give a summary. The first thing is a short-term challenge. Actually, at the moment, using your mobile phone, computer, you access a lot of Facebook, Google's. Actually, the data center is a bigger problem. With the laser, we can go to 10 gig. With the VCSEL, we can go over 50 gig, but you never go to 100 gig speed. So you need the transceivers to match the speed development for global data centers. And also, with this kind of over 100 gig, actually that's currently used with 3.5 transceivers. So with next step got to be 400 or 1 teragig. You need to put the optical and electronic together. So that's development for silicon photonics at the moment is a very hot topic. If you had a good solution, you can get a lot of money from venture capitals. The next long-term challenge actually is your computer problem, Postman's law. In 1965, Gordon Moore, he's a banker, he's not a scientist. He predicted your size of your transistor is in 24 months, start with, now 18 months, the size got to be half. But the number got to be doubled in same chip size. So, but the price is same. So at that time, anybody laughed because he's a banker, right? So, but he knows where the money comes from. Actually, it's true. After that, we call Moore's law to a lot of like economics, physics, and electronics. So from 1970 to around 2005, it's true. So you see, it's a linear increase, the number of transistors and the size slowly halving. So what's the problem, guys? At the moment, we use 22 nanometer or below. I think for all your mobile phones at the moment is 18 or 14 nanometer transistors. You think about that. After 12 months or 24 months, you should have a half your transistor size. Let's say now, last year, IBM talked about the 7 nanometer transistors, but they never put in your mobile phone because that's only done in the lab. What's the solution now? What's the problem? So first, you got to make a smaller transistor. It's very small, few nanometers, very challenging. And other things, the transistor, you're going to use quantum technology, not the conventional physics anymore. So you need a lot of new technology. And other thing is interconnector. At the moment, the limitation for your computer and your mobile phone, if you use it very long, especially when you watch video, your computer going to get very hot, eventually turn off. Because the copper interconnector is very thin. If you transmit it very fast, will be the bottleneck problem. The heat for the metal going to be very, very hot. Whereas because of all these problems, you need new materials, new chemistry, and a new development. So basically, guys, due to the transistor problem, a new technology came out a long time ago called nanotechnology. Actually, in physics, we call quantum technology anyway. But what's the solution at the moment? The solution at the moment, guys, in your computer or your mobile phone, you will tell you how many cores in your chips. That means they connect each chips. Instead of your double your numbers, they put more chips in your computer or laptop. So if you put the chip together, the connection is still copper wires and very thin. So that's the bottleneck part. So the solution will be, for multi-core chips, will be optical connector, like we use in optical communications. If we use optical connector, that will make the speed much faster and less heat generation. So with this idea, actually in the last 10 years, in other area come out called silicon photonics. So at the moment, if you go to a lot of conference, silicon photonics is very, very hot. Also, a lot of optical companies focus on this area. This one, that's the inter version of optical and electrical connection idea. This one from EU. So you say, doesn't matter what you do, you have to put the optical in silicon chips from a platform. So what's the challenge for silicon photonics, guys? Actually, in the last 30, 40 years, we have a lot of good waveguide. Silicon oxide make a very good waveguide. And also you have very fast modulators. Actually, you have very fast detectors, and also multi-channel communication and a coupler. The only one thing is missing, no what we call holy grail of silicon photonics, is electrically pumped silicon laser. So now I'm talking about what's the limitation for group 4 laser. So first thing is, for group 4 materials, guys, is indirect bandgap materials. So indirect bandgap materials for silicon actually is not efficient for making any emitter. So for 3.5, you have a direct bandgap. So for this one, you have 2 particle reaction. So you have photons and electrons. If for indirect bandgap materials, you have 3 particles. So you need in other one, phonon involved. So give you a simple example. For this one, you can easily get a peak second, at least 1 to 2 nanosecond speed, lifetime. But for this one, you get a millisecond. That's 10 to 6 magnitude difference. So even like that, actually in last 30, 40 years, a lot of big group still work on silicon laser, pure group 4 laser, like Intel and MIT. The first example actually comes from Intel, so-called Raman laser. Use silicon waveguide and use the optical pump laser, use Raman effect, they make a laser. So this one published in Nature at 2005, make a very big news at that time. But I'll tell you one thing, until today, this is still optically pumped. No electrically pumped laser. If no electrical pump laser, that means you don't solve the problem. You still need optical source. Very recently, actually this paper from MIT. So they use heavily doped germanium, so make a more direct bandgap like group 4 materials, and they make a first group 4 electrically pumped laser. So this one published in 2012. Actually, in the first year, the citation more than 200 times. So it's very important at that time, believe, but the threshold is 280 kilo per cent squared at 15 degrees. So this threshold, you never ever put in your chips because of power consumption. The power also is too low. That's 6 years ago, still, the threshold still over 200 kilo per cent squared. Very recently, in other new materials called germanium tin. So because you put a little bit of tin in germanium, you potentially make direct bandgap materials. So this idea makes a lot of group 4 guys very excited. Even for us, we also buy new AMB, try grow germanium tin. But actually you also have a problem. It's a larger mismatch. And also this paper published 3 years ago, roughly 3 years ago this time. Actually they get optically pumped about 90 Kelvin laser. Because the big achievement, first direct bandgap materials from group 4, they published in Nature Photonics. Until now, I see them last year, actually they only get into a little bit optical pump over 130 Kelvin. It's too far away for any laser in room temperature, and also very, very big challenge to make electrical pump device. So far guys, you see the best result from group 4 materials, so it's nowhere near in the near future you have any group 4 laser in your chips. So what happens with 3.5 materials? Because the challenge of group 4 laser, so that's a very good idea to put a 3.5 laser on silicon. Because 3.5 laser is with high speed and a lot of different wavelengths, but what's the main problem? If you grow 3.5 material on silicon, you will form 2 time defects. One is you grow non-polar materials, you grow polar materials on non-polar substrate. So the first layer is very important. So you have a phase problem. But the other one is the mismatch. So the lactic constant between silicon and majority group 3.5 materials is different. So you will have a disthreading locations. Even like that, actually in last 30 years, a lot of 3.5 quantum well laser put on silicon from a lot of different companies and universities. Due to time limited, I'll only give you a few examples of the best results I believe in the literature. The first one is from Japan. I have to say, I admire Japanese scientists and government. Doesn't matter how big a challenge, they still get money, get funding for the research. So this one published 2001. Actually, they get a room temperature CW laser. The threshold is 1.1 kilo per centimeter squared. It's not too bad, but the problem is the lifetime. So the device only work around 200 hours and they die. So with this kind of lifetime, you never ever put this kind of device in your practical system. The next one actually is from gallium antimony materials. Because gallium antimony is very soft materials. If you grow gallium antimony on very hard silicon substrate, you can have a misfit locations, and major in the interface. After that, you can have a good quality gallium arsenide on the top. You build up a laser on that. So even like this only CW work to 35 degree, and they never get lifetime report. But also, you do get the twins or thread in these locations in your gallium arsenide materials. Because the monolithic growth doesn't work for quantum wells, another idea come out from Europe and from US. I'll give you one example from UCSB, Santa Barbara. They collaborate with Intel. So that's their best results. So this uses wafer bonding. So you just grow 3-5 materials, you bond it on silicon, and you get the device working. So for individual device, the problem is the power is too small, and also they operate up 100 degree. The main problem for this one, actually, guys, is how to use bonding a lot of laser invested in chips. So 2 years ago, Intel announced 100G transceivers with 4 quantum wells, lasers on their chips after more than 20 years studies. But the main challenge is that's 100G, and what about the 400, 1 tera? So you got to put a lot of laser on. The yield is going to be very small, and also it's very difficult to make high density lasers. So far, I can say, guys, in all the literature, no one approach can solve the problem. About 10 years ago, I joined UCL, and we have one idea to put a quantum dot laser on silicon. Why quantum dots? I think that's the dense states. For quantum dots, you have a third function dense states. Each state, each energy level is separate. Because separate energy level can give you possible temperature-independent laser operation, and also with a very low structural current density. Of course, you can make a single photon device and also solar cells detectors. For us, we mainly focus on the laser part. How do you make 3-5 quantum dots? So actually, after the quantum well laser is successful, to demonstrate a lot of products, quantum dots is on the table for a long time. The first is man-made, use the H method. So with this method, you do have a low density, but also you have to introduce a lot of defects with the man-made. Not very recently, it's about 30, 40 years ago, and use SK mode, say for example, quantum dots growth. We can make very high density and low defects quantum dots or non-defects. Actually, this approach, I have to say, mainly developed by one of the pioneers from Yoffe Institute here. So basically what you do, you group indium arsenide on gallium arsenide here. So for first layer, you get a flat surface. With your further growth, you do have a 2D to 3D transition and get a low defect, low density quantum dots. These are mainly used for quantum single photon source technology. But your further growth, you get a very high density and uniform quantum dots. So we have here these quantum dots here. You can see indium arsenide have a big lattice constant. So you get a string relaxation and it forms 3D formed quantum dots. These quantum dots normally a few nanometer high, 20 to 40 nanometer wide. So if you do FM, see the surface more like a lot of yellow beans on the surface. I have an animation here, but I can't show here today, and basically tell you how to grow quantum dots on the surface. So I show the best results, I think, from 3-5 quantum dots materials. This is from QD laser. So for these quantum dots, guys, from -40 to 100 degree, the LI curve almost the same. That means you have a temperature-independent operation. After the 30, 40 years, work from all the scientists from the world, including Russia. And also, that's conventional indium phosphide quantum well laser. You can see from -40 to 85 degree, the LI curve is big difference. So that means for all your components with 1.55 operation, you need a cooler to make sure the laser operates at the same temperature to get the same performance. Actually, the half cost for your telecom components come from cooling. So just for the laser have stable performance. But if you use a quantum dot laser, you don't need a cooler. So get much cheaper. Also, they get a 10 gig at room temperature and the laser operating over 100 degree. So based on the achievement of quantum dot laser, we think quantum dots is a better solution to put on silicon. But another challenge is anti-phase domains. So with off-cast substrate, actually in the long history, we can grow no phase separation silicon materials. Another one is lattice constant difference. You have misfit dislocations. I'll tell you what's the approach we use to reduce dislocation density. So another very important thing, actually, we pointed out a long time ago why quantum dot laser is better. So put it that way, guys, doesn't matter what you do. You put 3.5 on silicon, you will have a higher defect density than native substrate. If like that, so if you have a quantum well, if one dislocation goes through quantum well, will kill your whole device. Because here we will become volcano, absorb all the carriers, and get very hot, even get a laser, you will not have a long lifetime. But if you use quantum dots, and if you have a defect across one quantum dots, the majority quantum dots still working. It's not damaged, because they are individually separate. So you get a laser, you potentially have a long lifetime. So basic simple idea, we work in the area. So the first thing we try is grow quantum dots on germanium. The reason is germanium and gallium arsenide have a very small mismatch, and also the virtual substrate is very low defect density virtual available. The other thing is you can, in nowadays, germanium IP layer was used in your CMOS called stringent CMOS. But the problem is self-terminate one more layer in the arsenic layer doesn't work, because arsenic at high temperature will diffuse in germanium, destroy the surface. When you first do the growth, you can see we use the arsenic pre-layer, the surface is very rough, like mountains in nanometer scale. And also you have an antiphase dominant form in the interface and go to the top. So what similar to do is use gallium pre-layer, and you grow the first layer gallium on the surface, stop the arsenic, go to germanium. If you get a very flat surface, you do have some interface defects because the mismatch is small, but you grow very thick, we will have relaxations. After that, things get easier. We just use the conventional 3.5 quantum dot growth grow on germanium. You can say, due to time limitation, I'm not going to go through detail, okay? So it's published anyway. So you can say, we don't have any defects with cross-section TM. And also, AFM quantum dots looks beautiful, uniform. And also PL, with optimal growth conditions, you can get almost as strong as ground native gallium substrate. With these results, we work with Sheffield at that time. We put 3.5 quantum dots laser on germanium. So this one, I have to say, guys, majority device I show here is very big. It's only for scientific, reasons, not for very practical application. So this device is a broader laser with a 50 micron stripe and very long, 5 millimeter long. So we make P contact at the bottom, ink at the top. Actually, the results is very surprising. It's the first time we get a CW operation and laser around 1.3 micron. So it's exactly the second window of telecom communication. And also threshold is very low. It's as low as the record result from gallium arsenide. And also the power is reasonable. We did grow quantum dot laser on gallium arsenide at that time to compare each other. Actually, the resistance is slightly higher because we have interface defects between gallium arsenide and germanium. And the only problem with the power is about half. Because it's off-cast substrate, the surface not very flat, and also the cavity not very perfect. You do lose some power. For the first device, we get CW operating until 60 degrees, and also. So after that, the next step is, if you get a laser on germanium, can you put on silicon? Because the goal is to put on silicon chips. So we did, we did get a 2 micron germanium buffer with a defect density of 526 by CVD from a friend. And after that, we use the same approach, put the gallium arsenide on the silicon. You can see, guys, actually germanium buffer on silicon is very mature now. If you grow germanium buffer, the defects is well confined in the interface. And also, you can see we also have a gallium arsenide buffer and the germanium buffer also confine defects very well. After that, we grow quantum dots. Actually, quantum dot looks good, and also PL's a little bit weak than germanium substrate because you still have defects in the buffer. Even like that, guys, they made some top contact for the laser device, also still broad area lasers. Even like that, guys, we get the first CW quantum dot laser on silicon, and the resistance is very high. We do have a P contact problem at that time at UCL. The defect density is very low. That's previously the record 210, we reduced to 64.3, and with a very good power for first demonstration. And also this one laser up 84 degrees, but CW only go to 30. The reason is a metal contact problem because we not sure how to make a p-time contact. I'm the first guy at UCL try to produce gallium arsenide-based device. After that, actually, the student graduate, we don't have further funding in the area. And Santa Barbara, Professor John Barber group, actually Professor John Barber group is one of the group leading on wafer bonding. They pick up our method, they produce a much better result. They get a CW laser around 120 degrees, and they get over 100 milliwatt room temperature. Also, they get, the first time, they get their results is better than their bonding results. So that's one approach. Actually, we do get the funding after that to 3-fiber quantum laser directly on silicon. So actually, 3-fiber ground silicon is a long time standing issue because you have two problems. One problem is anti-phase domains, and the other problem is threading dislocations. So in my opinion, the most difficult one is how to clean silicon oxide. We use direct heat up to 850 degrees, and we use arsenic 4 to suppress the APDs, and we use the dislocation filter layers to fill the dislocations. So first thing is nucleation temperature. So you need to grow gallium arsenide at a very low temperature, and you don't form a lot of defects, and also you get a flat growth. So we use this method, we get a very good quantum dots and a very good emission. So after that one, actually, we work the first laser. So we make the contact from bottom to top. The resistance is 15 ohm, so hardly be a diode. Even like that, we still get a laser at room temperature 1.3 the first time, and also the laser work up to 42 degrees. So the next trick is how to use other approach make the nucleation layer better. We use aluminum nucleation layers. Actually, you make a lot of defects confined the interface. So after that, we do get a good laser at 1.3 micron. Also, we push the laser operation up to 63 degrees. The other thing is, you do have a lot of defects. You need to study the dislocation filter layers to filter all the dislocations. So this one is not a particularly good sample because it's easy for TM guy to study the number of defects. So you can see when you start, you have 5, 10 to 9. Actually, after each thread dislocation layers, the defects, the dislocation density is reduced. Finally, we get a number around 3 to 5, 10 to 6 per centimeter squared. Also, for this time, we do proper P contact, N contact, and also we do top-top contact. So that's the first results we got at room temperature and with 100 milliwatt power and the laser operation over 100 degrees. The most important one, I believe, what we did is in other growth technique, so-called institute annealing. So basically, when you grow dislocation filter layers, normally after the dislocation filter layers, we grow gallium arsenide. For this one, we just give a few minutes more to anneal at a higher temperature. So you can see the dislocation annihilation rate is much higher. So that's the TM picture for the with the annealing. You can see after 4 repeated dislocation filter layers with the cross-section TM, we can't see any defects. It's about 10 to 5 range. So with that time, we have 2 postdoc works in fabrication. Actually, we can get a mirror-like fabrication and a top-to-top contact. So for this one, we get the first CW quantum laser direct ground silicon and a power over 100 milliwatt at 1.3 micron with a very low threshold. This laser CW operation up to 75 degrees and pulse go to 120 degrees. All the measurements are limited by our setup. It's not a really limited device. Also, we first time do a live test. For this live test, I have to say, this device is very big. It's not a commercial device in the process that you sell. It's not perfect. So also, we don't have an HR coating, so the device is very basic. So, until lifetime turned out was a surprise. The first 500 hours, the power reduced dramatically, the threshold current increased dramatically. After the 500 hours, it gets more stable. And we measure about 3,100 hours, the lifetime predict over 100,000 hours. So that's the first laser practical on silicon. So every time I give a talk, a lot of famous academics ask me, is anybody repeat the results? Did anybody repeat it? Actually, this year, from Santa Barbara, Professor John Barber group, they predict 340 years lifetime for their device, because their device is a proper fabricated in a commercial environment, very small HR code. But in the meantime, they also get a 12.5 gig bits per second speed. Also, very recently, CELATI worked with us. We also put on axial 100 substrate. So basically, it's already compatible with the CMOS fabrication technology. Recently, we worked with St. Petersburg Academic University here, and we made the first electrically pumped microdisc laser. So that's also a big achievement. Another thing I want to show you here, recently we worked with China. We made advanced laser chip. We make over 100 nanometer turning range laser with different DFB design. That means for one laser chip bar can produce very high band turn width. Finally, I show you the history of the threshold current density. I think you see a lot of names here from Russia because the achievement of Russian scientists in the laser field. In here, I put all the quantum dot laser on gallium arsenide on silicon. You can see the laser on silicon is approaching the best results on native substrate now. Finally, I give a summary. So around 2001, we use this approach. We predict quantum dot laser will be better alternative than quantum well laser. And at 2016, we demonstrate the first practical device on silicon. And also, recently, we demonstrated wide band range for laser bar. And also, this year, UCSB report the highest speed on silicon. So you can see, guys, all the 3.5 laser at the moment, quantum dot laser on 3.5 now is more or less to same performance on gallium arsenide substrate. So what's next? So the next thing is, can you put your laser into waveguide, become photonic interior circuit? Our plan is, we already demonstrate DFB laser. Also, we also demonstrate detector with a reverse bias with same materials. Well, what we need is a waveguide. How to achieve the waveguide? We have two approaches. One approach, we can use silicon nitride, silicon oxide. So this one much easier. You can just actual 3.5 materials, make a waveguide. The other one, we want to use the crystal silicon core. So this one more like you have the growing pattern substrate. You can see, guys, actually, this is a simple diagram. It's quite difficult for one group or few groups to achieve it. You need a lot of fabrication technique with the companies to achieve that. Finally, thank you for your attention. Also thank to my group guys to make these contributions. Mainly done by Smin and Jiang and Mingzhu here. I would also thank all the funding agencies support my work. Thank you very much.
Thank you very much. So one question, if any. No one. Okay. Thank you very much once again. Сейчас перерыв, и еще одна лекция будет, а потом будут презентации одноминутные. Спасибо.
to 3.
Коллеги, пока народ собирается, вот я хочу еще раз спросить, нет ли среди вас Татьяны Михайловой? Нет среди вас Татьяны Михайловой? Ну ладно. Уважаемые коллеги, нам пора начинать, так что я прошу всех вернуться в актовый зал. Okay, I suppose we can start. So, okay, let me introduce the next speaker. Professor Manfred Bayer from Technische Universität Dortmund. His presentation is entitled Interacting Rydberg Excitons in Copper Oxide.
Добрый день, and spasiba for the invitation to come here. It's always nice to come here, even though the weather could be a little bit better. So when I was first contacted, I was asked to talk about coherent spin physics, but I decided that this is hardly possible within half an hour, so I changed the topic and will talk about Rydberg excitons in cuprous oxide. And besides my main affiliation in Dortmund, I'm currently spending significant amount of time at the Joffe Institute, which will be sort of important for this particular topic. So first I want to acknowledge my co-workers. I won't go through the list in all details, but I want to highlight the cooperation with Marina Semina and Misha Glaser from the Joffe Institute, who provide very important theoretical calculations for us. And all the experiments are done at Dortmund by these guys, basically. So this is the outline of the talk. For those who are not familiar with the topic, I want to introduce the concept of Rydberg excitations. I apologize, this talk will not be so much about nano. It will be mostly about micron. And first I will start with introducing the concept of Rydberg atoms and what they are. Then I will turn to Rydberg excitons in this particular material system that I will be discussing, cuprous oxide. I want to highlight some crystal-specific features, turn briefly to excitons in magnetic field, and then come back to the main topic, Rydberg exciton interactions, and why they are interesting, in particular in the quantum regime. So what are Rydberg atoms? Rydberg atoms are atoms, could be hydrogen. Most people use alkali atoms, where you take the valence electron, the outmost electron, and promote this electron in a highly excited shell. So atomic physics people can go now to 100, 200, 300, 400 or so. And then you obviously have a hydrogen-like object, which has a core formed by the nucleus plus closed inner electron shells, and an electron sitting far outside. So the binding energy of this object can be obviously described by something which is very similar to the Rydberg formula, but in case of alkaline atoms, you do not have only the point-like nucleus, but you have the nucleus plus the inner closed shells, and they lead to some deviation from the 1/r potential that you know from the Coulomb problem. And these deviations are sort of summarized by this small correction here, delta L, which is a famous concept from atomic physics. It's called the quantum defect. And what is so interesting with these objects, if you look, for example, at the size of the average radius of an orbital with principal quantum number 100, you find that the average radius is no longer half an angstrom, but it's increased to half a micrometer. So your atom has become a mesoscopic quantum object. Yeah? Other interesting features are, if you look at the lifetime, for example, you know that the lifetime from the basic quantum mechanics lecture, the lifetime of an electron in a low-lying shell is roughly in the nanosecond range, but the lifetime scales with the third power, at least, of the principal quantum number. So it goes up from nanoseconds for n equals 100 up to milliseconds. And for people like me coming from femtosecond spectroscopy, this is basically eternity. Or if you look, for example, at the polarizability, if you expose your atom to an electric field, it scales like the 7th power of the principal quantum number. So it's dramatically enhanced by 14 orders of magnitude compared to ground state atom. And in particular, this property leads to giant interaction effects that I will address in my final point. So I guess everybody is familiar with the concept of an exciton. Just to introduce it very briefly to set the stage, sort of, we are talking here about bulk semiconductors, boring bulk semiconductors, intrinsic semiconductors, no intentional doping. And what we do is we have a filled valence band, we have a filled conduction band, we take a weak laser and promote electrons from the valence band to the conduction band, or formulated in a particle-like description. Photons are coming in, generate an electron-hole pair. Locally at a particular position, we have two charges which are oppositely charged. or two particles which are oppositely charged, so they interact with each other, and this is a hydrogen-like complex, and we would describe the binding energy by this formula. Just to remind you, how do we typically describe the exciton in such a bulk crystal? You are, of course, familiar with the hydrogen problem here. You find that for hydrogen, the Rydberg energy is given by this formula, which gives you 13.6 electron volts. And the key thing is now that we sort of comprise all the many-body environment that the crystal provides into two quantities. These are the effective masses and the dielectric function. The dielectric function sort of screens the color interaction, and also the effective masses, which are summarized here in this reduced electron hole mass. It also reduces the Rydberg energy, so that you find typically in standard 3-5 semiconductors, or also in cuprous oxide, binding energies on the order of tens of milli-electron volt. I want to point out that still in this particular material, which is a cubic crystal with highest possible symmetry, these are isotropic quantities, so you still would expect that you have rotational symmetry and that angular momentum is a good quantum number. In particular, you would also expect that angular momentum is degenerate. So in our case, cuprous oxide, these are the masses. It's one of the rare cases where the hole is lighter than the electron. The electron mass is roughly the free electron mass. The hole is roughly 0.6, the free electron mass. Dielectric function is 8.5, and if you plug this in, you find a Rydberg energy of 86 milli-electron volts, so pretty high. But I want to point out that this hydrogen-like description has limitations. So if you look, for example, at the wave function of the exciton, it's given by this hydrogen-like envelope, but this has to be multiplied via in a crystal and not in vacuum by the Bloch states of the electron and of the hole, so that your wave function is not as smooth as a hydrogen-like wave function would be, but it has this sort of spiky nature here, which also tells you immediately that angular momentum or rotational symmetry cannot be preserved per definition. It depends whether you see the consequences. I will show you the consequences of this symmetry breaking, but in general, rotational symmetry is obviously broken for such a spiky wave function. Okay, exciton concept, just to make the relation to Joffe in St. Petersburg, introduced 1931 by Frankel at the Joffe Institute, just on the opposite side of the street. Later on, a few years later, it was extended by Vanier and Mott to what we know as Mott-Vanier excitons. Excitons I'm discussing here are also Mott-Vanier excitons with some deviation, but the principal concept goes back to Frankel. And if you look for excitons, maybe the most prototypical semiconductor in terms of optical properties is gallium arsenide. So for gallium arsenide, if you plug in the material quantities, you find that the Rydberg energy is only 4.2 milli-electron volt, and then you go to a theoretician and ask, how would the optical spectrum look like, at least at low temperatures, and then you find this answer. So if anybody tells you that the optical absorption is proportional to the joint density of states of electrons and holes, this is never true, because you have exciton effects, and this is the single particle expectation here, the dashed line, which shows the joint density of states, the square root of E-like dependence, but this is never what you observe. What you observed is shown here by the dashed line. Due to the Coulomb interaction, a lot of oscillator strength is shuffled from far above the band gap towards the band gap, so that you see in a bulk semiconductor a step-like dependence, and below the band gap you see these bound states of the excitons, and for gallium arsenide, due to the small Rydberg energy, these are 3 discrete lines, not more. These are the corresponding experiments done a long time ago. This would be the single particle expectation. The band gap here is at 1.519 electron volts. You see that above the band gap, you indeed have a flat absorption, and below the band gap, you see 1, 2, 3 different lines, which are the bound exciton states. All the chunk down here is due to defects. So experiment matches pretty much a theory. But one has to say that excitons were not discovered in gallium arsenide, but in cuprous oxide, and this lasted roughly 20 years since the first proposal by Frankel, by Yevgeny Gross, also at the Joffe Institute, and I want to point out that he used artificial crystals, and this was his absorption measurement. performed at 1.3K, and you see here the n equals 2 exciton, 3, 4, 5, 6, 7, 8. So he pretty much discovered already the hydrogen-like exciton series. So this is a setup of GROSS. I was told that originally it was at the Joffe Institute, but then it was, I do not know, stolen or whatever. Now it's at the St. Petersburg State University, and you can still sign up for lab courses there and perform experiments at this setup. This is just to show you the spectral resolution that they had at this time. So it was sort of a miracle that they could resolve these discrete lines. This is a setup that we are using in Dortmund. I don't want to discuss the details. This is a picture of the setup, and just to highlight what is important, we use frequency stabilized lasers, and we stabilize the emission line width, these are CW lasers, down to 10 femtometers. So you need extremely stable lasers. This is a crystal that we are studying. In contrast to GROSS, who used an artificial crystal, we are using natural crystals. So no nanotechnology or fancy stuff. This crystal is probably 100 million years old. It's from Africa. We bought it on eBay or so, and then we cut out small slabs from this crystal, mount it strain-free into a crystal holder, plug it into a cryostat, and start to measure. That we know, or that we have extremely high quality crystal, this we were aware already in 2007 by studying the ground state exciton, the so-called para-exciton. It's formally forbidden, but you can slightly activate it by applying a magnetic field. Without going into the detail, this is the absorption line that you get. So we just record the absorption by scanning the laser across this resonance, and you see the para-exciton resonance, and the line width that we record here is 84 nano-electron volts. Here we have a nano, yeah? I told you that we don't have too many nanos in my talk, but this is a nano-electron volt, and I think that this is still the record line width ever recorded on a exciton in a semiconductor. So this is cuprous oxide. Very briefly, we have BCC lattice of oxygen atoms and the FCC lattice of copper atoms, and they are shifted by a quarter of a space diagonal relative to each other. And simply speaking, it's the simplest case of a two-band semiconductor. So you have here your conduction band, it has even symmetry, you have your highest valence band, it's also a single band, and we are interested in the excitons involving the lowest conduction band and the highest valence band, and these excitons form the so-called yellow exciton series, just for historical reasons. The conduction band is mostly formed by S-like or S-type atomic orbitals, the valence band by D-like atomic orbitals. And there is obviously an angular momentum difference of 2. This tells you already that electric dipole transitions for which the selection rule is written down here are not possible. But if you involve the envelope wave function, you can make these states at least weakly allowed. Obviously, you come down from the angular momentum difference of 2 down to 1 by involving an envelope wave function of p-type. So what we can excite, and this is also what Gross excited, were p-type excitons. And this was also the reason why he could not observe an n equals 1 exciton, because there is no n equals 1 p-type exciton, obviously. So no group theory today. These are the measurements that we performed then, something like 3 or 4 years ago. I have to give credit to our Russian colleagues from St. Petersburg. They wanted to make an exhibition to honor Gross for the discovery of the exciton, and they were approaching us with all your fancy lasers. Could you study the exciton series in these days and see where you end up? So what we do is we record the absorption by scanning the laser from lower energies to higher energies. We indeed can observe with these lasers the 1s exciton. I told you that this is dipole forbidden. That's true, but it is quadrupole allowed, so in next higher order, and this is why we can observe it with these fancy laser systems. Then we scan to higher energies, roughly 1 LO phonon above the 1s exciton. Phonon induced or assisted absorption starts. This is not important for this case. Then at some point we find the 2p exciton and then the 3p exciton, and don't go into too many details here. If we then sort of zoom in into the series, we find here n equals 2, 3, 4. We zoom in here on the high energy bank, find 5, 6, 7, 8. This is where Gross had to stop, but we can continue all the way this series up to n equals 25. Now you might say, what is n equals 25? Atomic physics guys can go up to 500. Well, what plays in our favor is that the Bohr radius is 1.1 nanometer in our case. So if you plug in just the numbers and take the formula from the hydrogen atom for the average radius of an orbital with principal quantum number n, you find that these excitons have an extension of, on average radius of 1 micrometer, so an extension of 2 micrometer, which means that they are extended over 10 billion crystal unit cells. So these are huge quantum objects moving in this crystal on a tremendous background of charges, but nevertheless they are stable. Okay, so then you can elaborate on the properties of these excitons. Without going into details, you can check, for example, the binding energy, and you indeed find that the binding energy, at least with this resolution that we have here, follows an n to minus 2 law, but only on this energy scale and with this resolution. If you look a little bit more into details, this is basically a close-up of the spectra that I showed you already. The dominant features here are the p-type excitons, n equals 4, 5, 6, 7. And then we found on the high energy side, systematically starting from n equals 4, tiny lines. If you zoom in here, you find that these lines are triplets. The line width is remarkably low. It's on the order of a microelectron volt. And in fact, these are F excitons. So you see that you have a splitting between P and F excitons. This tells you already that what you know from hydrogen, degeneracy of angular momentum states, is no longer true in the crystal. Moreover, the F excitons are split, which tells you also that angular momentum is not a good quantum anymore. And this is also the reason why we observe these states. Because angular momentum is not a good quantum number in a crystal, these angular momentum states become mixed, and some oscillator strength is transferred from the P excitons to the F excitons such that we can observe them. So clearly there are differences from the simple exciton description that you learn in solid state physics. Yeah, hydrogen model is not in all cases sufficient. You can model this also. I just want to point out the details of this modeling. This is the Hamiltonian that we use. It's already a very much simplified Hamiltonian. We also did full spin density functional theory calculations. These are the black lines here, but for really calculating the exciton problem, we sort of use fits to these black lines shown by the blue and by the red lines here. And these fits are basically can be described by this formula, which is the Hensel-Suzuki Hamiltonian. And just to point out, this would be the hydrogen problem, and all the chunk that comes at the end is basically the valence band. And you need to include all this chunk in order to really describe your exciton spectrum qualitatively. Okay, maybe I skip this. Why is it so interesting to put these excitons in a magnetic field? Well, it was already very helpful for atoms, because when you apply electric field or magnetic field, you induce very characteristic energy shifts as you vary the field strength, and moreover you split also degeneracies. And therefore this was also very helpful in exciton spectroscopy. Why is it particularly attractive to do this compared to atoms? Well, the reason is again that we can truly enter the high field regime, because our Rydberg energy is much, much smaller. For example, if you want to apply a magnetic field, the characteristic energy scale for applying magnetic field is obviously the cyclotron energy. So H bar times electric charge times B, magnetic field strength divided by the mass. And typically for semiconductor, this gives you a millielectron volt or so times the magnetic field strength. So if you want to enter the high field regime, which is defined by the fact that the cyclotron energy is much larger than the Rydberg energy, for atoms you need to apply 10,000 Tesla, which you find in white dwarf stars, but not really on Earth, while in our case we just need to apply a few Tesla. And this is of course standard today. And the expectation that you would have in this particular regime where magnetic confinement is much, much stronger than Coulomb interaction, the expectation is that you just observe Landau level transitions. And this was also our expectation. This is the result. I have to give credit here to the PhD students. This contour plot may look trivial, but in fact it's composed out of 12,000 spectra in order to get the proper resolution. So the PhD students were locked for 4 weeks in the lab. They got some food from time to time, but they were recording this series continuously in order to get this contour plot. What you see here is starting from n equals 4. This is zero magnetic field. So here we would have our hydrogen series, and then we apply a magnetic field, and you see basically first a high energy shift, which is a diamagnetic shift, and then you see basically a spin splitting. Below this red line, which is below n equals 6, your spectra look more or less okay. And above the red line, all hell breaks loose. As you can see, for example, this is a close-up, a small zoom into a small area here. And actually what we found, we wanted to go very fast to interaction phenomena, but then we got stuck here. What happens here is that you have no longer a regular motion that you could easily describe by Schrödinger's equation and solve by Schrödinger's equation, but you have quantum chaos here. Quantum chaos is a sort of a little bit ill-defined field, much less clearly defined than classical chaos, where you have Lyapunov exponents and all that stuff. But here it's not very well defined. You can basically judge about whether you have quantum chaos or not quantum chaos by looking at 2 different lines. And you have a regular motion when you bring these 2 lines in resonance, for example, by varying the magnetic field. And when they cross each other, then you still have regular motion. You are in the quantum chaos regime once you bring 2 levels in resonance, and you find in all cases, really in all cases, you find anti-crossing. And this is exactly what we find here. So crossings are no longer observable, you have only anti-crossings. And this is a criterion for quantum chaos, and actually it's a very interesting quantum chaos, because in this particular case, I cannot go into the details, all anti-unitary symmetries are broken. And this is what you even do not find for atoms in magnetic field. You find it for fundamental interactions like the electroweak interaction. There you have also all anti-unitary symmetries broken, but for studying electroweak interaction, you have to go to CERN or large-scale colliders. Here we can do it basically in the lab. Okay, just for the record books, the highest Landau level that we can observe at the moment is n equals 75. This would correspond to an exciton extension of 10 micrometer, but this is only for record books. Okay, maybe I skip also this and come to this interaction question. So why are these Rydberg atoms so interesting for atomic physics people? The reason is the following. It's called the Rydberg blockade. Imagine that you have a cloud of atoms. Or in our case, it could be also a cloud of excitons. Imagine that you have this cloud of atoms, and you take then a resonant laser which excites one of these atoms into a Rydberg state. So you have a cloud of 10,000 atoms or 100,000 atoms in a volume of 10 micrometer or so, and you excite only one of these atoms into a Rydberg state. And then you want to repeat this step. You want to take the very same resonant laser and excite a second atom into such a Rydberg state. And this is no longer possible because of the huge interactions that these atoms show. So once you want to excite, you have one atom in a Rydberg state, and you want to excite a second atom into a Rydberg state, you find that due to the interaction of these 2 resonances, the resonant line is strongly shifted out of the resonance profile of your laser. So for such a cloud, you can excite one atom into a Rydberg state, and a second excitation is not possible. This means that by exciting only one atom into a Rydberg state, your whole cloud of atoms has become transparent. So it's really a switching on a quantum level. So we were sort of looking for the same thing, and we found indications for this already at the very beginning in our very first paper. When you look, for example, here at the absorption series, these are extremely low laser powers. We even increase the focus of the laser spot in order to reduce the laser powers into the nanowatt regime. If you increase slightly the laser powers here, you see that the high energy lines are disappearing here, while the the exciton lines on the low energy side, the energies remain stable and also the line width does not broaden strongly. In fact, this is exactly the consequence of the Rydberg blockade. What happens here is that we excite already Rydberg excitons, and because of the presence of these Rydberg excitons, you can have no longer absorption by this particular laser here, and your crystal has become transparent. In order to understand this a little bit more, we have integrated over each individual line here, and what we have plotted here is the peak area below each line as a function of the laser power. And you see, as you increase the laser power as shown here, all of these lines start to decrease. What we did then in a very first approximation, because we had no idea, actually nobody knows exactly how to describe exciton-exciton interactions. This is a terribly complicated problem, and we are just working on this. But just to get a first idea of what is going on, we fitted these data by this formula, where your absorption at a particular laser energy using a particular laser power is given by the absorption spectrum recorded if you would apply zero laser power. This is obviously not possible, but let's say very, very low laser power so that we have no Rydberg blockade effects. So this is the ideal absorption without interaction effects divided by unity plus the laser power times Sn. And Sn is a phenomenological quantity which tells you how strongly does such an exciton block the absorption. And when you determine these Sn quantities from the fits, you find this dependence on the principal quantum number. So shown are here the states from n equals 12 up to 24. This is a double logarithmic plot, so you see that the data points lie on follow a power law. And it looks not very interesting, but when you look at the numbers here, this blockade efficiency increases from n equals 12 up to n equals 24 by 3 orders of magnitude. And when you fit then a power law to the data, you find that the blockade efficiency scales with the 10th power of the principal quantum numbers. So this is an extremely strong scaling law. We developed also some theoretical model for this, which basically tells you that this blockade efficiency is proportional to the lifetime of an exciton times the size that this exciton has. How big is it? And from this you find indeed a good agreement with the experimental result. But at that point, we were sort of surprised that it doesn't matter what interaction you assume between the excitons. So we use, for example, a van der Waals interaction. It gives you this n to power of 10 dependence, but you can similarly use a Förster type of interaction, which has a totally different scaling dependence with the separation between the excitons. It also gives you an n to the power of 10 law. So this n to power of 10 is an extremely stable quantity. And until recently, it was not clear to us how to describe exciton-exciton interactions. But this is clarified now. These are very recent results where we extended the experiment such that we use 2 color pump probe experiments. So we have 2 of these frequency stabilized lasers, and we fix the photon energy of one of these lasers to the n equals 16 exciton, to this state. And with the other laser, we scan across the absorption spectrum. For low powers, you see, this is a differential absorption basically. You see basically that when you pump here at the n equals 16 state, very slightly, with very low power, the absorption is slightly increased. But once you increase the power slightly, you see that all the peaks basically go into the negative range, which means all of them are bleached, and we get the Rydberg blockade for all these states. Now then you have to zoom into one of these set of lines which corresponds to a particular principal quantum number. And there you find a very interesting behavior. This is basically the set of spectra that you record. In this case, it was the n equals 8 state for pumping at n equals 16. And you see that the energy of this line which becomes blocked does not shift at all. And also, what is very characteristic, that all spectra show one point where they cross, irrespective of what pump power you are using. And in the literature, you find a lot of different possible interactions between excitons, like exchange interaction, defect scattering, plasma shifts, first dipole-dipole, van der Waals interactions, all is possible. So we checked all these mechanisms by calculating the exciton spectrum. I have no time to go through the details, but we found out that only a single interaction gives you this characteristic behavior, that the absorption line becomes bleached without any energy shift, and that you have this universal crossing point here, and this is the van der Waals interaction. Yeah, and with this, basically, I don't go into the details. This is heavy quantum optics calculations. You can describe all your spectra. So the result of these studies is that we finally understand the interaction between excitons, and this is a van der Waals interaction. There are a lot of other interesting features here. For example, if you zoom in here in the n equals 10 case, you see that the main absorption lines becomes blocked when you increase the excitation power. So, but simultaneously on the high energy side, increased absorption shows up. And from this we uniquely conclude that our interaction between excitons is repulsive. It's not an attractive interaction, but it's a repulsive interaction, and there are many more things that need to be studied. For example, if you look at different angular momentum of the excitons, these are the p excitons, these are the f excitons. Here you have even some indications of h excitons. Again, we increase the pump power here from low densities up to high densities, and you clearly see that the f excitons go first into the blockade while the p excitons are still absorbing. So there are still a lot of details which need to be understood, and then we can go further. This is just an outlook of what we want to do. I hope that I convinced you that these are interesting objects, because in contrast to atoms, we can sort of study the whole series of Rydberg excitons by scanning just a single laser. We can enter the high field regime, but we have also disadvantages. For example, this very complex band structure of the valence band, or the many interactions that you simply have in a crystal, like with photons, with phonons, and all that stuff. What we are currently doing, for example, we go to time-resolved studies in order to demonstrate Rabi oscillations. The line width of these lines is extremely small, so they have pristine coherence properties. We have been working a lot on understanding this Rydberg blockade that I discussed, and this is very important for our next steps, because what we want to do is very similar to what atomic physics people are doing. We want to use counter-propagating laser beams in order to generate potential landscapes, and because of this Rydberg blockade that I just discussed, it is possible to load into each of these traps just a single exciton. And now that we understand the interaction between these excitons, we can sort of start to construct something like a quantum simulator and solve problems that are hopefully helpful for somebody. With this, I want to stop. Thank you very much for the attention. Nicht intention.
Time for one or two short questions, if any. Okay, just one from my side. Okay, please.
Is there something which prevents Bose-Einstein condensation, say, repulsion or something else?
No, Bose-Einstein condensation is a very long topic on this material system, and it has been mostly studied for the ground state. And for the ground state, we understand by now that it's Auger processes between the excitons, where one exciton is emitted at lower energy and the other one is sort of ionized, which prevent you from crossing the threshold to a Bose-Einstein condensation. There are a lot of claims about exciton Bose-Einstein condensation in this material, but I do not trust them, frankly speaking. For these highly excited states, you also cannot cross the threshold to condensation. But what should happen is what atomic physics people claim as a Rydberg ice-like states. This is not really a Bose-Einstein condensate, but you might imagine, and they could never demonstrate it, that when you pump your crystal with a proper number of excitons, due to the strong interactions, repulsive interactions between them, they do not collapse, but they sort of form a crystal-like exciton state. And this is also on our agenda to demonstrate this. But similar to Bose-Einstein condensation, the experimental signatures are not fully clear.
let's thank the speaker once again. So, закончились приглашенные доклады. Сейчас мы переходим к презентациям молодых ученых. И я с удовольствием представляю Андрея Липовского, профессора, который будет вести презентации в лифте. А пока, значит, у нас такая пауза творческая. Еще раз хочу спросить, Татьяна Михайлова, если здесь есть, просьба подойти ко мне, потому что там была какая-то перепутка с бейджами, и, значит, мы постараемся ее устранить.
Значит, сейчас мы с вами начинаем нашу элеваторную секцию. Значит, ну и все будет как в лифте. Не только быстрое выступление, но и быстрый вход и выход из лифта. Поэтому я буду называть выступающего и следующего за ним с просьбой сразу спуститься, чтобы быстро заменить его на этой короткой остановке лифта. Значит, презентации ваши все здесь подготовлены. Ну и поехали. Значит, первым у нас приглашается, я прошу прощения, если я буду неправильно произносить фамилии, чтобы не извинить за это. Значит, первым приглашается Владимир Гришняков, приготовится Юлия Клунникова. Значит, микрофон здесь лежит.
Хорошо. Здравствуйте. В данной работе выполнены ДФТ-расчеты прямых фазовых переходов графеновых слоев L6 и L4-8 в полиморной разновидности графана. Установлено, что из графита на основе слоев L6 при давлениях от 57 до 71 гигапаскаль наиболее вероятен синтез кубического и гексагонального алмаза. Полиморф алмаза с наиболее напряженными структурами можно получить из тетрагональных графеновых слоев L4-8 при давлениях от 32 до 52 гигапаскаль. Если вам интересна данная работа, подходите к секции 1.02. Спасибо.
Спасибо. Значит, я предлагаю, может быть, даже исключить аплодисменты в лифте, поскольку лифт уйдет. Вот, поэтому, пожалуйста, Юлия Клунникова, приготовится Илья Петренев.
I would like to present my work. We receive titanium oxide films on sapphire substrates for as gas-sensitive materials. We receive some experimental and simulation experiments to improve the steam quality and to receive gas sensors with better characteristics. Thank you very much.
Спасибо. Пожалуйста, Илья Петренев, приготовится Марина Дерменева.
Здравствуйте, меня зовут Петренев Илья, я представляю Уральский федеральный университет, и предметом моей работы являются наноструктуры на основе анодированного диоксида циркония. По этой тематике существует огромное количество работ, огромная часть из них посвящена исследованию температурных характеристик и их влиянию на получаемую структуру. Так, самой малоисследованным фактором, на мой взгляд, является такой фактор, как разница температур между анодом и электролитом. И, собственно, этому работа моя посвящена. Как показало мое исследование, действительно, разница температур имеет огромное влияние на получаемую структуру. Поэтому, кому это было интересно, мой постер 1.04, приходите на постерную сессию, будет очень интересно. Спасибо за внимание.
Спасибо. Пожалуйста, Марина Дерменева, приготовится Максим Беленков. Выступающих, прошу обращать внимание, что там есть пульт, с помощью которого можно переключать слайды, лежит на кафедре. Так. Видимо, Марина Дерменева отсутствует. Пожалуйста, Максим. Значит, следующий у нас Максим Тингаев.
Мой доклад посвящен исследованию фторографена и его полиморфных разновидностей. Исследование фторографена производилось методом рентгеноструктурного анализа. Также вы можете видеть рентгенограммы и изображения слоев на рисунке 1 и таблица 1. Также были проведены исследования 5 полиморфных разновидностей фторографена, которые вы можете наблюдать на рисунке 2. Далее у нас были проведены исследования зоны и структуры данных 5 разновидностей фторографена и на рисунке 1, на рисунке 3. И также вы можете наблюдать плотность электронных состояний на рисунке 4. В результате работы было получено, что запрещенная зона находится в пределах от 3 до 4,2 электрон-вольт. И образец, который мы исследовали в данной работе на рентгене, он соответствовал первому структурному типу. Вот, если вам интересна данная работа, подходите к секции 1.11. Спасибо за внимание.
Спасибо. Выступает Максим Цингаев. Следующий Андрей Лозовенко.
В моем докладе представлены результаты исследования гибридных углеродных SP2 плюс SP3 структур, получаемых при совмещении фуллеренов C20 и C24. Расчет геометрически оптимизированной структуры был выполнен методами теории функционала плотности. Была рассчитана структура и свойства этих двух фаз. Кроме того, были рассчитаны зонные структуры и плотность электронных состояний. Было установлено, что у фазы, сформированной на основе фуллерита C20, запрещенная зона отсутствует, а у фазы из фуллерена C24 она составляет 1,76 электрон-вольт. Энергии сублимации совпадают и в диапазоне значений, характерных для углеродных материалов, устойчиво существующих при нормальных условиях. Спасибо за внимание. Секция 1.12. Спасибо.
Спасибо. Значит, Андрей Лозовенко выступает. Приготовиться, пожалуйста, Александре Старниковой.
Добрый день, уважаемые коллеги. Предлагаю вашему вниманию доклад на тему «Синтез нанопроводов Висмута для применений в термоэлектронике». Работа выполнена в лаборатории нанотехнологий Белорусского государственного университета информатики и радиоэлектроники. В работе показана методика темплейтного синтеза массивов нанопроводов Висмута для, собственно, применения в термоэлектронике. Рассмотрена методика управляемой модификации темплейтов для формирования нанопроводов с требуемыми размерами. И рассмотрены особенности электрохимического осаждения висмута в поры темплейтов и определены оптимальные условия для воспроизводимого синтеза. Более детально приглашаю к постеру 1.15. Спасибо за внимание.
Спасибо. Пожалуйста, Александр Старников. Приглашается Данила Сивков, следующий.
Добрый день, меня зовут Александра Старникова, я из Южного федерального университета. Мой доклад на тему исследования газочувствительных свойств массивов наностержней оксида цинка на угарный газ. Нашими коллегами из Казахстана были получены массивы наностержней оксида цинка, которые наносились на кремниевые подложки. Мы анализировали, направляли газ СО в закрытую камеру при температуре нагрева подложки от 150 до 200 градусов. Концентрация угарного газа была от 100 до 1000 ppm. Сначала мы ждали, пока произойдет насыщение угарным газом, после переключались на воздух, производили продувку воздухом и так повторяли в течение 2-3 раз. Скорость подачи газа составляла 0,3 литра в минуту. После мы делали продувку азотом и выяснили, что на чувствительность угарного газа влияет наличие кислорода в воздухе. И тем самым мы измеряли чувствительность газу и воздуху. Все. Можете подойти к стенду номер 1.19. Спасибо.
Спасибо. Сейчас выступает Данил Севков, приглашается Василиса Никеева.
Dear colleagues, hello everybody. The high-resolution X-ray diffractometry is an effective and non-destructive method for crystal structure investigation. To determine crystal structure from the scattering intensity distribution, the inverse problem should be solved. This nonlinear problem depends on many independent parameters, and the parameter space has a large number of local minima. And the genetic algorithms has shown their high efficiency for searching solutions under such conditions. So in my work, the differential evolution algorithm, one of the genetics ones, was used. The experiments of X-ray scattering in the silicon crystal was simulated within the dynamical theory of diffraction. The dependencies of various residual functionals on the algorithm cycles were calculated. So for more detailed information, welcome to the poster session, poster number 145. Thank you.
Спасибо. Пожалуйста, Василиса Никеева. И следующим будет Алексей Маслов у нас выступать. Сейчас мы найдем презентацию вашу, да?
Good afternoon, ladies and gentlemen. My name is Vasilisa Nikeyeva, and the title of our work is Perovskite, a new material for thin film solar cells. Metylammonium lead trihalide or perovskite has generated significant interest for its unique properties, low cost, and facile deposition techniques. In this work, the growth of single crystal perovskite, its structure, and some properties have been investigated. The short scheme of synthesis you can see on slide. Also, there is photo of the crystals obtained. Structural analysis of crystals were performed in Siberian synchrotron and terahertz radiation center. The composition of crystals was confirmed by X-ray photoelectron spectroscopy. The next result is a heat pattern obtained from a clean perovskite surface, and the last figure is photoconductivity spectra in different temperatures. If you want more details, please find me at the poster number 307. Thank you.
Спасибо. Выступает Алексей Маслов. Следующим выступает Дмитрий Кудряшов.
Уважаемые коллеги, мы представляем работу, связанную с решением прикладной задачи по поводу разделения в пространстве областей рекомбинации, в которых рекомбинация доминирует. В общем-то, мы решаем задачу определения доминирующего из ряда членов, который фактически ограничивает общее время жизни и эффективность фотоэлектрического преобразования солнечного элемента на основе гетероперехода аморфного и кристаллического кремния. Мы взяли за основу работу рабочей группы из лаборатории НРЛ, в которой была описана подобная модель и учитывалось 3 области рекомбинации. Однако в современных солнечных элементах с гетеропереходом необходимо учитывать рекомбинацию и в объеме аморфного кремния, в который здесь не учитывается. Кроме того, рекомбинация в аморфном кремнии может описываться не только по статистике Шокли-Холла и Рида, но и с точки зрения моделей оборванных связей. Поэтому мы учли в данной работе этот недостаток. Мы описали механизм рекомбинации с точки зрения как Шокли-Холла-Рида, так и с точки зрения дефекта Pull Model, так называемый, и привели к подобному виду, в результате чего мы предлагаем способ обработки экспериментальных данных, основанный на измерении коэффициента идеальности и температурных измерений напряжения холостого хода, в результате чего мы можем выделить и количественно определить доминирующую область рекомбинации, которая ограничивает эффективность фотоэлектрического преобразования в гетеропереходных кремниевых солнечных элементах. Плакат 3.14. Спасибо, коллеги.
Спасибо. Выступает Дмитрий Кудряшов, приглашается следующим Александр Козловский.
Добрый день. Я представляю лабораторию возобновляемых источников энергии Санкт-Петербургского академического университета. И на данной конференции я представляю одну из наших работ, выполненных в последнее время, разработка солнечного элемента на основе оксидных гетероструктур. Основной материал — это, конечно, оксид меди первой валентности, а также в качестве эмиттера используется оксид цинка. Было проведено теоретическое моделирование, которое показало, что максимально можно достичь КПД порядка 12% на такой системе. Скажу, что сейчас японцы уже разработали солнечный элемент на основе оксида меди с КПД 8%, но их технология заключается в высокотемпературном росте оксида меди, порядка 1000 градусов. Моя работа позволила немножко снизить температуру роста до 450 градусов, и в данной работе представлены результаты по структурным и оптическим свойствам данного оксида, а также по солнечному элементу, разработанному на данной системе. На данный момент рекорд 315 милливольт, полученный в нашей лаборатории. Подробности, пожалуйста, слайд 3, постер 3.17. Спасибо.
Спасибо. Значит, сейчас выступает Александр Козловский, следующий приглашается Марина Фомина.
Добрый день, меня зовут Александр, я из Саратовского государственного университета. В моей работе исследуется влияние освещения кремниевой подложки в процессе адсорбции катионных анионных полиэлектролитных молекул на вольфорадные характеристики структуры диэлектрик-полупроводник. ФХ таких структур сдвигается влево либо вправо в зависимости от адсорбции катионных либо анионных полиэлектролитных молекул соответственно. И величина этого сдвига коррелирует с концентрацией адсорбированных ионов. Так, было получено, что фотоассистированная адсорбция молекул фермента глюкозооксидазы в случае использования подложек P-типа приводит к уменьшению, а в случае использования подложек N-типа увеличению сдвига вольфорадной характеристики по сравнению с темновой адсорбцией. Это означает уменьшение в первом случае, увеличение во втором, концентрация молекул фермента на поверхности кремниевого преобразователя, что подтверждается данными атомно-силовой микроскопии. Ну и данные исследования могут быть полезны при создании чувствительного слоя ферментов для потенциометрических биосенсоров. Постер 7.06. Спасибо за внимание.
Спасибо. Сейчас у нас выступает Марина Фомина, приглашается Амар Лалвани. Амар Лалвани is the next.
Здравствуйте, уважаемые коллеги. Представленная работа посвящена исследованию структуры циркониевых покрытий, полученных на титане в результате электроискрового легирования. Морфология покрытия была сформирована в результате переноса капель, термической обработки и частичного окисления. Исследовано влияние технологических режимов легирования на морфологию покрытия и химический состав. В результате установлено, что полученное циркониевое покрытие является структурно гетерогенным. Данное покрытие может применяться на изделиях медико-технического назначения, таких как имплантаты, остеофиксаторы и так далее. Рекомендованы рациональные режимы более выраженной структуры поверхности с содержанием циркония 16,21 атомарных процента и содержанием кислорода менее 5,15%. Спасибо. У меня все.
Спасибо. Амар Лалвани. Следующая Надежда Беглецова.
Здравствуйте. Our topic studies the investigation of the photolysis spectra of quantum dots monolayer. The formation of quantum dots monolayer by Lingomer Plot Jet technology This technology gives us the possibility to control the thickness and the distance between interparticle. The deposition was done on different composition type of substrate. We found that the fluorescence depend on the composition of a substrate because this will influence the transfer energy from quantum dots to the substrate. Also, we studied the influence the distance between the layer of quantum dots and substrate by inserted insulator liquid crystal and with increase the distance between quantum dots and substrate, this will enhance the photoluminescence spectra for quantum dots. This is our topic, and thank you very much.
Спасибо. Значит, сейчас Надежда Беглецова и следующий Павел Голубков.
Добрый день, меня зовут Надежда Беглецова, я представляю Саратовский национальный исследовательский университет имени Николая Гавриловича Чернышевского. Моя работа посвящена изучению влияния температуры водной субфазы на возможность формирования монослоя лингмюра на основе наночастиц меди, стабилизированных поверхностно-активным веществом додецилсульфатом натрия. С увеличением температуры водной субфазы, можно следующий слайд? С увеличением температуры водной субфазы мы можем видеть, что происходит уменьшение площади, приходящейся на монослой. Это может быть связано с увеличением скорости растворения поверхностно-активного вещества, а именно додецилсульфата натрия. И полученные исследования, они важны для формирования плотно упакованных высокопроводящих пленок на основе наночастиц меди по методу Лингмюра-Блоджет для устройств микро- и наноэлектроники. За более подробную информацию подходите к постеру 7.11. Спасибо.
Спасибо. Пожалуйста, Павел Голубков, следующий Иван Егоров. И просьба более тесно общаться с микрофоном. Будет
Здравствуйте. Представляю вашему вниманию доклад на тему применения методов теории надежности для анализа процесса микродугового оксидирования. Как известно, в настоящее время одним из основных недостатков процесса МДО является недостаточность сведений о том, как влияют параметры технологического процесса и другие влияющие факторы на свойства МДО покрытий. Для решения этой проблемы было решено использовать методы теории надежности и качества, такие как диаграммы Сикавы и диаграммы связей. Буду рад побеседовать с вами у постера 7.14.
Спасибо. Пожалуйста, Иван Егоров, следующий Павел Полканов.
Здравствуйте, уважаемые коллеги. Мой доклад связан с созданием инструментов из различных материалов, в которые впоследствии будут подвержены химико-термической обработке. В данной работе представлено соединение титановой пластины с хромистой инструментальной сталью при помощи контактной сварки, которая позволила достичь высокого качества соединения, прочности и твердости самого изделия. Спасибо.
Спасибо. Пожалуйста, Александр Фомин. Следующий будет Сергей Мизинцов.
Здравствуйте, уважаемые коллеги. В данной работе с помощью индукционной термической обработки производится упрочнение инструментальной стали и хромоникелевой стали. В результате данного упрочнения твердость возрастает инструментальной стали до 11 гигапаскаль, а твердость хромоникелевой до 12 гигапаскаль. На рисунке представлены слева микроструктура поверхности, а справа наноструктура. Спасибо за внимание.
Спасибо. Пожалуйста, Сергей Мизинцов, следующий Владимир Кашура.
Здравствуйте, уважаемые коллеги. Я представляю Технический университет из Саратова. Мы занимаемся термической обработкой тугоплавких материалов. Это титан, тантал, цирконий. И в данном исследовании изучена слоистая структура танталового покрытия на титановой подложке. Далее подвергалась эта вся система индукционно-термической обработки в диапазоне от 600 до 1200 градусов Цельсия. В результате изменяется структура поверхности, изменяется морфология, и, конечно же, это влечет за собой изменение физико-механических свойств. Меняется твердость, ну и, в частности, для таких структур можно получать достаточно твердые системы, которых твердость может превышать даже 30 гигапаскаль. И, конечно же, это может использоваться для медицинских изделий и, если это комбинации и с остальными структурами, для инструментального производства. Спасибо за внимание.
Спасибо.
Постер 1.14.
Спасибо. У нас случился небольшой сбой. Сергей Мизинцов выступал у нас или нет? Ясно, хорошо. Так, тогда Сергей Мизинцов предлагается выступить, если... Угу. Следующий Владимир Кашура.
Снова здравствуйте, уважаемые коллеги. В данной работе с помощью электроискового легирования производится упрочнение поверхности титана, технически чистого ВТ1.2.0. Суть обработки заключается в последовательной обработке титановым электродом и графитовым электродом. В результате данной обработки твердость после титанового электрода повышается до 10 гигапаскаль. После обработки графитовым электродом твердость повышается до 20 гигапаскаль. Слева на рисунке представлена морфология поверхности после обработки титановым электродом, а справа после обработки графитовым электродом. Спасибо за внимание.
Спасибо. Пожалуйста, Владимир Кашул. Следующая Елена Пошивалова.
Также наша группа занимается изменением поверхности инструментальных сталей. И вашему вниманию представлен метод нанесения карбида титана методом электроискрового легирования на быстрорежущую сталь, что позволило достичь высоких эксплуатационных характеристик инструмента. И также достигнута высокая адгезия между инструментальной сталью и материалом карбида титана. Спасибо.
Спасибо. Пожалуйста, Елена Пошивалова. Следующий Дмитрий Королев. Елена Пошивалова.
За Елену Пошивалову также я рассказываю. Наша группа еще занимается модификацией пористых покрытий. В данном методе представлена катодная модификация пористого элемента, которая позволила достичь высокой концентрации серебра в пористом покрытии. Концентрация достигала до 1%. Спасибо.
Спасибо. Пожалуйста, Дмитрий Королев, следующий Богдан Бородин. Так.
Здравствуйте. В последнее время значительное внимание привлекают исследования аккумуляции электрического заряда в наночастицах золота, встроенных в пленки диэлектрические пленки. Такие пленки считаются перспективными для использования в качестве плавающих затворов в элементах компьютерной флеш-памяти. Цель настоящей работы – экспериментальное исследование возможности создания одноэлектронных элементов памяти на базе наночастиц золота в порядках 2 нанометров, встроенных в пленки стабилизированного диоксида циркония. После инжекции электронов в наночастицы золота наблюдалось локальное изменение поверхностного потенциала. Динамика инжектированного заряда анализировалась методом Кельвин-зонд-микроскопии. Значение потенциала уменьшается со временем. Это связано с уходом электронов обратно в подложку. Результаты работы показывают возможность использования исследований пленок в качестве плавающих затворов. Спасибо.
Спасибо. Пожалуйста, Богдан Бородин. Следующая Ханна Захлебаева.
Hello, ladies and gentlemen. The theme of my work is Kelvin probe microscopy of molybdenum diselenide on graphene. This system has emerged as an attractive for novel nanoscales electronic devices. Dependence of the work function and surface potential at the number of layer was shown in this work. This data can be important for detecting a number of layers molybdenum diselenide. I'm glad to see you around my stand 732. Thank you for attention.
Спасибо. Пожалуйста, Ханна Захлебаева. Следующая Оксана Шинкаренко.
Здравствуйте еще раз. К сожалению, коллегам приехать не удалось, поэтому я представляю совместную работу лаборатории нанотехнологий Белорусского государственного университета информатики и радиоэлектроники и кафедры химии Белорусского государственного технологического университета. В ходе данной работы методом ионного наслаивания были сформированы гетероструктуры сульфида цинка и сульфида станума на подложках и из различных, на различных подложках, таких как пористый анодный оксид алюминия и островково-сетчатые структуры оксида титана. В ходе работы проведены исследования фотовольтаических характеристик и исследованы температурные зависимости поверхностного сопротивления полученных наноструктур. Данные гетероструктуры могут использоваться для фотовольтаических сенсоров, датчиков. Спасибо за внимание. Более детально постер 7.33.
Спасибо. Сейчас Оксана Шинкаренко выступает, и приготовится Мария Тутовой.
Здравствуйте еще раз. Our topic for Shinkarenko, influence of pH surface on the monolayer formation of pyrene and pyrene in isosonic acid matrix. The aim of this work is to get structure of graphene, but first step we study the formation of monolayer for pyrene. Pyrene has a similar structure for graphene, but need to do some study to get a similar structure for graphene. We studied the formation of pyrene by ligmar plugit technology. By ligmar plugit technology, and we studied the influence of pH. We found with the changing the pH, the occupied area of monolayer increased because this will get the molecular part will increase the ionization and will increase the repulsion force between them. But we have a problem here. The monolayer has not stability over time, missing layer. So the figure P, we have a composition pyrene with arachidic acid. This arachidic acid will support the monolayer and will increase the stability over time. Thank you.
Спасибо. И наш последний доклад в этом сессии, пожалуйста, Мария Тутова.
Hello, dear colleagues. Color generation on the metal surfaces under laser exposure is the unique phenomenon. The most common explanation is based on connection between color and phase composition of the generated films. However, phase compositional analysis is a complicated and expensive process. As an alternative option, we present a calculational method based on chemical thermodynamic approach. According to this method, color generation can be described by a chemical reaction, and the formation of the most probable compounds has the lowest level of the Gibbs energy. We tested our method on titanium nitride coating, and the results of our calculations are in good agreement with the phase compositional analysis. During experiments, we revealed one mode that can change the color of the titanium nitride coating from golden to blue by changing only the number of laser passes. This phenomenon Что мне сделать, чтобы анимация была? Мне нужна анимация на следующем слайде. Еще раз? Sorry. Sorry. This phenomenon is described by presented animation, and for detailed information, I invite you to visit my poster number 710. Thank you.
Спасибо. We have one more elevator presentation. And welcome. And I suppose the lecturer will present himself.
Ladies and gentlemen,
I'm Adam Gajdoš from Czech Republic, from Brno University of Technology. And I would like to present my article named Isolation and Optoelectronic Characterization of Silicon Solar Cells Microstructure Defects. Next slide, please. Next slide. Okay. My motivation for this work is that silicon solar cells are still most used photovoltaic devices, and defect-free wafers are highly requested. However, some defects may appear in a fabrication process, so I use some defect characterization methods, just like current voltage measurement, electroluminescence, near-field scanning microscopy, and energy dispersive spectroscopy. And for defect isolation, I use focused ion beam. Left image shows current voltage characteristics before and after isolation. So this is a brief summary of my article. Thank you for your attention.
Спасибо большое всем выступившим в этой сессии. Я хочу несколько объявлений сделать, они касаются таких организационных дел. Значит, обед, он запланирован на 2 часа, поэтому сейчас, значит, есть время тем, кто не повесил свои постеры, их повесить. Те, кто не взял талоны на усиленное питание, это, значит, можно сделать. Это вот, значит, у организаторов там какое-то количество их остается, и поэтому, значит, вы не стесняйтесь, их берите. Те, у кого обед в академическом университете, у меня просьба обратить внимание на время, потому что, значит, там помещение ограниченное по объему, и, значит, здесь организовано питание в 2 смены. Те, у кого обед в политехническом университете, там, значит, поскольку надо прогуляться по парку, подышать свежим воздухом, зато там